So I hope you can all hear me okay. Hello everyone, welcome to the 2021 meeting of the Royal METSOC Atmospheric Chemistry Special Interest Group. My name is Ryan Hosseini, I'm one of the co-chairs of the ASG, along with Paul Griffiths from Cambridge University. I'm based at Lancaster University. So for those of you that may not have attended one of these meetings before, we hold annual events, or we aim to hold annual events, normally in person, and we invite a series of distinguished speakers to tell us about their research, and we arrange the meetings according to topical themes in atmospheric chemistry that appeal to quite a broad audience, and our themes typically have a meteorological spin as well. So the theme of this year's meeting, as you can see, is the air quality and climate impacts of COVID-19 lockdowns. Now, I'm sure we can all agree that COVID and COVID lockdowns have had a profound impact on lives and livelihoods worldwide, and indeed continue to do so. But from an atmospheric science point of view, there are a range of complex responses to reductions in emissions during lockdowns that require detangling and explaining. And sometimes that's not straightforward given natural variability and meteorology and such like. And I think today the speakers are going to touch upon those interesting issues amongst other areas. So without further ado, we have two sessions today. This one now in the morning, which runs to 12:45 when we have a break. Then we have an afternoon session also, and the meeting closes at 4. Given that this meeting is online, that's made it easier to get international speakers, which is fantastic. So we're pleased to be joined by them. So I'll just say thank you for joining us today, and thanks to the speakers in advance. And I think I should have gone through these opening slides too quickly. So here's a bit of housekeeping. Please ensure that your microphone is muted and your video is switched off. There is this chat area to the side where you can post your questions, and Paul and I will monitor that and ask the questions to the speakers at the end of each talk. And please, if you're not a Royal METSOC member, consider joining the society for these benefits that are on the screen. So thanks everyone. I'll pass over to Paul now, who will chair this morning's session.
Thanks, Ryan. I would say our morning session is loosely based around observations. I'd like to ask our first speaker, Stuart Grange from the Swiss Federal Institute for Material Science and Technology, to take the stage and to present on the impact of COVID-19 lockdowns on air quality in European urban areas. Over to you, Stuart.
Well, hello. I hope everyone can hear me okay, and greetings from Zurich. So yes, this is a piece of work that it's my pleasure to present this work, piece of work that myself and some colleagues at EMPA in Switzerland and some colleagues at the University of York, specifically Wolfson Atmospheric Chemistry Laboratories, after the first COVID-19 lockdown. So this analysis is more or less confined to the first half of 2020. So, okay, so as the introduction was very much apt at saying, the COVID-19 lockdowns really were unprecedented for most people, everyone in my world anyway. And one of the biggest results was the population mobility was reduced by very significantly between March and May 2020. And we saw that the lockdowns, this reduction of mobility, reduction of economic activity, had many positive environmental effects, including CO2 reduction or CO2 emission reductions and reductions of air pollutants. And in here, this piece of work was very much an urban focus, but in European urban areas. And when I say European urban areas, we really tried our best to have a pan-European analysis. And we focus primarily on nitrogen dioxide, or NO2. And for those which are a little disconnected from the air quality world, this really can be considered the traffic diesel pollutant, and ozone. So this is tropospheric ozone, ground level ozone, which is a secondary pollutant, meaning it's not emitted, it's generated in the atmosphere. So the mobility was drastically altered during these first lockdowns, and because of this drastic alteration of people's transportation and mobility, you'd expect that this would be present, where you'd see this effect in the air quality monitoring data record. So some of the best ways I've seen of showing this mobility reduction is these data. So these are from the Google Mobility set. So it's anonymized data, and this is for Europe. And we can see that we go along, and so at the beginning, so this will be the February of 2020, and then these lockdowns were announced around about this time. There's some variation in the different countries, but we just see this big plunge of things like public transport, retails, and workplaces. So we're looking at 2/3 at least at an average, and you can even see a bit of panic buying here, which was prevalent in some countries.
Sorry, Stuart, I should say we can't see your pointers.
Okay,
so,
okay, not a problem.
Just make sure. Yeah.
No problems. So you can see that the mobility was very different. And just as a little bit of a, just a heads up, I suppose, is this idea of a lockdown is very variable depending on what people are talking about and what country you're dealing with. So we can use these same data and we can sort of classify, subjectively classify from a strict lockdown to a non-strict. So for example, in Switzerland and Germany, we were never restricted in the way that the British were or the French were. So there are some differences around what actually the policy stringentness or strictness were. So we wish to say, well, if what we need to do is when we want to compare what was observed in 2020, we really need to come up with an idea of what would have been the air pollutant concentrations if the lockdowns did not occur. So we can say that this is a business as usual scenario or a counterfactual or a prediction. So I'll use the word counterfactual here. So this idea is that we have what actually happened and then a good idea or a good estimate of what would have happened without this intervention, without the lockdowns. And we can just simply compare those. Unfortunately, this is not a particularly simple task technically because the weather situation, the meteorological conditions in the first few months of 2020 were actually very unusual. And it must be said that this is not the case everywhere in Europe. I remember I did a talk this year in Scotland, and I was looking at Edinburgh and Glaswegian data, and the observations actually look pretty similar. But for example, in Switzerland, we saw quite a different situation in the weather in 2020. So this is a bit overplotted, but if we go to the left-hand side, we've got air temperature, and we've got 4 groups, 4 years, 2018, 19, 2020, and 2021. And this is the average for between February and May. And you can see that 2020, we're quite a bit warmer than the other years in that example. And then on the right-hand side, we have wind speed. And again, you see a higher wind speed, average wind speed for 2020. And if anyone's done any wind dispersion modeling, this is very important for air pollutant concentrations. So this idea that we need to take into account meteorology or weather when we're doing our predictions is very clear. So to do this, we applied a random forest model, and this is a machine learning decision tree method. And we did this for 3 pollutants, NO2, so nitrogen dioxide, ozone, and what we call total oxidant. Total oxidant is just the sum of NO2 and ozone. And it operates as, it's not really a pollutant in itself, but it's sort of a reservoir idea, this idea that you may have these different pollutants going up and down, but total oxidant may remain the same because it's the sum of the 2. We included almost 250 monitoring sites, over 100 urban areas, and 34 countries were included. So we did do our best to make this a European analysis. And just for urban areas too, cities or towns. And we check these models. Obviously, you need to do a model validation procedure. And then because the training period ended in 2019, or the beginning of 2020 actually, we can just ask the model to predict forwards in its perspective, but based on the observed meteorology, the observed weather that was experienced in that year. So this gives you this idea of the counterfactual, a predicted time series which the observed can be compared with. And then to actually isolate the times and the magnitude of the difference or the divergence between observed and predicted, we used a kind of sophisticated change point model. We just didn't want to say, look at the time series and say, oh, it looks about this date and about this amount of change. We formalized that. And just to be clear again, is we ended this analysis, the observations ended at the time for this analysis at the end of July 2020. So this is the counterfactual. So this is an example of London Marylebone Road, a infamous or well-known site, depending on your perspective. And you can see this is 2000, and this is the beginning of 2020. That's plotted. The dashed line is the date of the British or the United Kingdom's lockdown date, and the top line, this red line, shows the counterfactual or the predicted concentrations, but the blue greenish line is what actually happened. And you can see that these two, that the counterfactual on the top, it still has a lot of the structure of the observed concentrations, but you just have this big offset, and that's because the emissions were low. And so you can just compare these. So that's the predicted versus observed. So the results, what did we find? Well, NO2 at a European level decreased by about a third. That was the main thing. So a reduction of about 33% of NO2. And if to put this in context, if you were to say, well, because NO2 across Europe is decreasing over time, and if you took the observations between 2010 and 2019 and then did a trend analysis, so you say, well, what is the average change per year? That third of reduction was about 7.6 years of reduction. So it's a very significant drop. But on the other hand, or conversely, ozone, so the secondary pollutant, increased between 20 to 30% depending on site type. So there's quite a big difference between an urban traffic site and an urban background site. And OX, total oxidant, did not really change. So there was some minor changes, especially at the traffic sites. So these sites, these monitoring sites were at the curbside, at the roadside. And we can interpret this that perhaps primary NO2 emissions were perturbated. So this idea that generally most diesel vehicle will emit mostly NO, but a little bit of NO2. So you end up with this idea that perhaps if you remove some types of vehicles differently, so passenger vehicles compared to heavy duty vehicles, this ratios will change, and that might be what we see. So if we just focus, so this is what it looks like at a European level. If we focus on the right hand side, the top brown line is the ozone divergence from the counterfactual. The dashed line would be the observed and predicted would be the same, and NO2 is this reduction. The NO2 is the grey time series, or the aggregation going negative. And you can see that ozone returned to about what you'd expect in that time period, so between February and July, but NO2 still hadn't quite got to business as normal at the time of the analysis ending. And then so for these change point models, so I said we objectively defined a model which would give us the dates and the magnitude of the change of the divergence. And for NO2, this was very clear. So you could you have a table of national lockdown dates and a table of the change point model dates, and they matched very well. Ozone, this wasn't quite as clear, but then because ozone is a secondary pollutant, so it's generated in the atmosphere, there's sort of chemistry must happen in the atmosphere. It depends on the precursors, so you'd expect there'd be a little less of a direct linkage. And we can see on so this is a representation of the change point models. So we can see on the left hand side, this is for the UK sites included in NO2. You can see that the change point analysis actually found, the change point models are done many times to make the robust analysis. And you can see that depending on which sampled set you take, you actually end up with two answers here. This is very interesting because in the UK there was a week before there were effectively 2 lockdown dates. There was one date when the leaders said, all right, we can't go to the pub, and then a week later it was a more what we'd consider a lockdown now. See, and the change point models actually see this in the observations, which is very interesting. In ozone, it's much clearer after, so it took a couple of days for the change point to be identified. And this just allows us to simply come up with tables like this. So this is just a subset, but it's a bit tough without the cursor here. But if we go down to the left-hand side, we can see Switzerland. If we go Switzerland traffic, then there's a bold percentage change in the 4th column. It's a negative 17% for NO2. If we go across, we've increased ozone by 22%. But then if we keep going down the table to the UK traffic, we can see NO2 decreased by almost 51% and ozone increased by 50 or 46%. So there were rather big differences across different European countries and different sites, which is what you'd expect. You know, Switzerland is less polluted in terms of these pollutants than the UK on average. There were different lockdown stringencies. So there's a lot of variation, and those tables are in the paper for a particular site or for a particular country anyway. So our implications were, well, we had a decrease of NO2, but a decrease by 1/3, but ozone more or less increased to match this. And this links to this oxidator, this total oxidant, the OX. So because the OX is the sum of NO2 and ozone, the actual reservoir of this total oxidant didn't really change very much. And then this pattern represents the general trend. So if we look at Europe or any country really across in Europe, NO2 is going down in urban areas, in some places faster than others, but ozone is starting to creep up. So we can just say that COVID-19 lockdowns, they were exacerbation of a lot of the trends that we've seen in the last decade or two. For me, one of the most surprising things was this complete replacement of ozone when NO2 decreased. And this really points towards that the ozone cycle is, or the ozone generation in an urban area is a very complicated chemistry. There's a lot of components, but it means that another precursor, probably VOCs or volatile organic compounds, are the limiting factor for ozone generation. So this could be important for management. And if we sort of push these observations or these points forward into the future, this can say, well, we're likely to switch off NO2 sources because our fleets are very quickly heading to electric vehicles. But this may increase, that may give rise to a greater problem with ozone in urban areas across Europe. So those were our conclusions at the time. And then I think, however, when we hit after the July, or the end of July was when the analysis period ended, if we start taking in the entire year and say, well, what's happened? The situation does look a little more complicated than those implications, those conclusions we concluded at the first half of last year. So the next natural question is, what occurred when we considered the entire 2020 year? So we can do a similar analysis, but this time we also want to include aerosols, so PM10, PM2.5. We want to include other VOCs, volatile organic compounds, because these are questions that are always asked with these sort of analysis. Well, what happened with PM? What happened with my particular VOC of interest? And so we can do that, and it's just, I think there's a bit more complication around the technical side of things, because if we take PM10, for example, an aerosol measurement, an aerosol pollutant, we have processes such as Saharan dust events. This is these events where we just get dust over Europe. It happens in Switzerland on average once a month-ish. But there's no such thing as an average Saharan dust event. It kind of depends on what event happens. And so this sort of machine learning statistical model will always struggle to represent those processes well. So we need to have a bit more of an idea. We have to be a bit clearer on the limitations of the models if doing these extra pollutants. It's the same with VOCs. Some of these VOCs are very sensitive to solar radiation for generation secondary, and if the models can't capture these vastly nonlinear generation processes, they will not perform very well. But the idea is that perhaps we would just want to take 2020 means and say the observed and the predicted. What do we see? So this is an example of this analysis, and these have been plotted from the left to right from increasing pollutants on the NO2 scale. So you can see that if we go to the top, the far right, we've got NO2, Nice Promenade. So in France, there's a site quite polluted with NO2, and you can see that the red line, the red dot is what the counterfactual would predict, but then the observed is what actually happened. So you can just say, well, what was that difference? And I think in 10 years' time, when we look back, this is the kind of analysis which will be important. We'll say, well, in our databases, we have different, our 2020 annual means look a little anomalous. What was the effect of these lockdowns? And that's what we're currently working on at the moment. So like I say, further work and investigation, we'll really need to find out some of these model deficiencies or limitations, I suppose. So, and when we consider 2020 as a whole, I think the situation is a bit more complicated than what we first reported. So if we take the entire year, some locations we're seeing ozone is actually maybe higher, lower than it was, than the counterfactual prediction would predict. This is in contrast of what we saw more or less everywhere in Europe at the first half of the year. So it will be interesting to see for the rest of the speakers. I'm sure this will be brought up today. But so there is a bit more complication. It just sort of shows, I don't think we were premature with conclusions, but perhaps the implications we came up with, do need a bit of, in hindsight, we can improve them or make them a little more specific for the time period. So our conclusions, so I've got 45 seconds to go. So when we consider the first half of 2020, we saw these NO2 reductions of about 1/3 across European urban areas. At the same time, ozone increased, and then this is this idea of OX, this total oxidant, this reservoir, the sum didn't really change. So this has implications for air quality management. I think we really demonstrated that this idea of prediction using these random forest machine learning methods plus a change point analysis was very robust. And then if we go to the next step, which we're working on, and we consider the entire 2020 year, the situation is probably more complicated. And so I'll leave with that. And I just want to thank my co-authors again. Publication is there, it's an ACP. And I think that's it. Thank you.
Thank you, Stuart. Very clear and interesting presentation. Maybe I could ask the first question. The shift in composition from NO2 to ozone, did you consider the health implications of that change in the NO2 to ozone ratio, maybe?
We have not done that, no. That is, that's quite a different field. But that is something, yes, because you have these trade-offs, and ozone has more effects at a different scale. So you've got crop yield issues and other climate effects that NO2 doesn't. So to do that would require probably a different research. But yeah, sure. I'm sure that has been done. Maybe not in Europe, but in the US, I'm sure.
Thank you. David Stevenson has a question. Does your analysis, which is to say that the OX was unchanged, suggest that the VOCs didn't change much?
Well, I don't think the OX being unchanging suggests the VOCs didn't change much. It just means that the balance between the ratio between this reservoir idea, this total oxidant, you've got different the ratios of ozone, the main components ozone and NO2 really did change. And I can tell you, based on other analyses with the VOCs, some VOCs were very much changed, but others others were not. And this is because VOCs is such a massive group of compounds, and they really you really need to be specific about which which VOC you're dealing with, because some of them are emitted biogenically, some of them are personal care problems, some of them come from fuel. It's a complicated area.
Thank you. We have another question from Roy. He asks, I think it's a he, did the double lockdown breakpoints show as clearly in the raw mobility time series data as in your NO2 data?
No, it didn't. The mobility data was not that clear. You could probably squint and say, oh, I'm kind of seeing it, but it wasn't a clear feature. These, because if you say, if we sample the observations, you just end up with two answers based on the divergence of the observed and predicted. But the mobility data didn't seem to predict, or didn't seem to display that feature very clearly at all.
And then I think the final question that we've got time for is from Marlon, who notes that OX didn't change much, but there's a lot of variation in the results that you presented, and asks, isn't this due to compensation when performing the aggregation at the European level? Yeah,
that could be. There was a like, I'd say that because all these models were done at site level, and we just systematically aggregated up. But yes, you are very correct. There was a rather large variation of results and conclusions, and especially the deltas were rather different. And this just reflects the different environments, the different levels of pollutants, the different policies which were applied at these different countries, different cities at some points. But I don't think that would, because the modeling was done at the lowest level we have, the site level, I don't think that will, I don't think the systematic aggregation would alter, those conclusions.
Thank you.
Okay.
Actually, it's tremendously hard to pull out a consistent picture from such a broad range of data. So, very interesting study. Thank you.
Thank you.
Okay.
I will leave stage now. No problems. Thank you very much.
So our next speaker is Zongbo Shi from the University of Birmingham. Zongbo, are you ready?
Yes, can you hear me?
Yes, thank you. So it's over to you.
Excellent. Thank you very much. So I'll just try to see. Right. So what I'm going to be talking about is an abrupt but small and unexpected changes in surface air quality. We call it attributable to the lockdown effect. So this work is mostly done by Tongbo Song, which is the second author. It's also in the audience. So I'm just really giving this sort of ideas behind this. But first of all, thanks to Stuart, who have given a lot of backgrounds, which I don't need to give anymore, and even including the methodology. So thank you, Stuart. Right. Now, we have all seen all sorts of news about the impact of lockdown, and this is the first one is really interesting, where people have been looking at the Indian Gate, where one photo taken during pollution time and another one during our clear day, and you can see the huge differences. And I mean, you can't really attribute that to lockdown, but it's a interesting photo to show the effect. And there is also the BBC News shows the air pollution levels plummet across UK due to lockdown. If we look at, can we see that one? Now, how do we quantify the real lockdown effects? This is methodologically, there are different methods to do this. One of the ways is to use air quality modeling, where if you look at the meteorological impacts, and then you can then start to attribute the real changes in air quality to lockdown effects. And what we are looking at here, including what Stuart has been talking about, is based on observations. So one of the ways is to compare this year's data with previous year's data as what the BBC has been reporting. So in that BBC News, we can see that this is the 2019 levels during 17th March to 5th of April, and the bottom shows the 2020 during the same period. And if you take away the concentration during the lockdown period, from 2019 to 2020, you get the difference, and this is what you get from the data, and you can see those huge changes in concentrations. And by the huge changes, you can see, of course, this is nearly 50% reduction in comparison to 2020 during the lockdown effect. But this isn't a right way to do that. So what Stuart has been suggesting is that let's predict those in 2020 using meteorological conditions. So that's one of the ways to do it properly. And there are also ways that you can compare the concentration of air pollutant, whether it's from the satellite or from the ground level, before the lockdown began and after the lockdown began. And then you can see the difference, as you can see here. This is the difference, and you can see, okay, well, that indicates some level of impact from intervention, or in this cases, the lockdown. But again, there are, I'll explain this later, what are the problems with these methodologies. Now that is, as Stuart has been talking about, this weather impact. And in a short time scale, the pollution levels or air quality is dominated by meteorological variations, not changes in emissions, such as those associated with the lockdown. As you can see here, this is the data from Wuhan. One of the papers that has say that after the lockdown began, the pollution level has been reduced. The NO2 levels has reduced by 90%. But that reduction, you cannot attribute that reduction to lockdown. That is largely driven by meteorology. So similar to what Stuart has been doing, is we using this random forest modeling, and we did this for 11 cities rather than all the different size and different across the Europe, or so we look at different countries, Asia, Europe, and America. And we use the same R package. We adjusted the code to for our own purposes, and we again do similarly as the original Grange paper. We do side by side, and we use local meteorological data, and we also did the high split model and clustered the back trajectory, and we use the ERA reanalysis data set as well. So in general, our model performance are relatively good. If you look at the R, mostly is more than 0.9. Our colleagues have, in a previous paper, our colleagues have done WRF CMAQ model. That's in another paper in where we did this in Beijing. So it's not for this particular study. So the purpose is just show the performances. If we look at the monthly observed PM2.5 and the monthly observed PM2.5, the CMAQ model have given a good prediction, if we including all data, and our random forest model is performing really, really well. with an R-square of close to 1. Interestingly, if we take in those single data point away, which is in January, the performance of the CMAC model has been going to extremely poor, I would say, but it doesn't really affect the random forest model. And the other kind of models that is being used in literature, including the regression models, they often are not very good, where your R-square quite often goes to as low as 0.27. Now, in terms of methodology, what we did is similar to Stuart. I'm not going to go to details here. What we see here, you can see this is the measured concentration of NO2, and the shaded area indicates the weather effect. And what you can see here, this is the same Wuhan data. We can see the huge decrease after the lockdown began, but that decrease is mostly due to meteorology effect. You got a really poor meteorological conditions before the lockdown began, and a much better conditions when the lockdown began, and that together makes us a huge decrease in NO2, but only a very small proportion of this can be related to the lockdown mediated emission changes. Now, the other thing we can clearly see here, this is a relatively sudden changes in concentration in NO2 and sudden increase in concentration in ozone. This is, we believe, due to photochemical steady state, essentially when the, for example, the road traffic NOx emissions reduces. When NO reduces, there is emission reduces, there is less nitrogen oxide in air to titrate ozone, so the ozone concentration goes up. And you can see that is synchronous, is essentially happening at the same time. But what you can see here, the OX concentration doesn't change much at all. You have a really small dip and then it doesn't change. This random forest model is not a total black box. It can be used to investigate what controls the air pollution variations. In this case, is, for example, the temperature controls the ozone variations, which makes sense. So let's see some result here. The first is the de-weathered NO2 and ozone. As we already showed before, we are seeing sudden drop of nitrogen dioxide around lockdown days, but not as big as the NOx, where we have showed, which is understandable because of the titration effect. And we have seen a sudden increase in ozone around lockdown date, which is due to photochemical steady state. As I said earlier, you got less NO in the air, so you have essentially the ozone is going to go up. Interestingly, we see some more gradual changes in NO2 and ozone in London. That may be partially related to the anticipation effect, and the what Stuart suggested about earlier is the initial ban on going to pubs, etc. in the UK. What we should also be bearing in mind is there is an increasing trend in ozone in previous years. For example, in 2018, we can see those ozone concentrations goes up from the winter to the spring as well, and you can see that also in Wuhan, London, Paris, and Los Angeles. Essentially, you'll see those general trends, which is happening almost everywhere in the globe. But if we look at the PM2.5 de-weathered concentrations, we didn't see much abrupt changes, unlike the NO2 and ozone, which we did see abrupt changes. We didn't see that, except in Los Angeles. And we also see that, sudden changes in Beijing and Wuhan a few days after lockdown, not immediately after lockdown. We have seen the PM 2.5 went up in London and Paris, and we have been trying to understand those. It's potentially related to the larger scale circulation, the pollution from Europe, for example, which the model didn't capture very well. So it didn't de-weather that very well. But we have seen large increase in the PM 2.5 to PM 10 ratios in Paris, or the PM 2.5 to CO ratios, suggesting an increased secondary formation or large transport of fine particles. There is some studies suggesting an enhanced oxidation capacity, leading to increase in the initial PM 2.5 in Beijing, and we didn't see much evidence of OX increases. No, we don't have, for example, the hydroxyl radical observations, so we don't really know. But whether there is a definitive answer about enhanced oxidation capacity is, I personally feel maybe there needs more studies. The OX, the de-weathered OX didn't show much changes, as Stuart suggested earlier, so I'm not going to show them in much more detail now. What we are arguing here is that because of the emission and chemistry changes from the winter to the summer and by different years, we can't just simply use the de-weather data to tell us whether to quantify the impact of the lockdown. Now, the concept here is that over the year, so let's say this is January. So from January to April, we can see May. The maximum ozone concentration we're seeing here is in May. So if we're looking at the pollution or ozone levels in April comparing to before lockdown, let's see, 15th of March, naturally that's going to be much higher ozone concentration itself, whether or not you're going to have a lockdown. So this is one point. There's a seasonal changes here. So if you're comparing the concentration before and after lockdown, then you're really not looking at the real changes attributable to lockdown. You're looking at something that's partially happening laterally. And the second point here is we can see there's a general increasing trend in ozone, for example, in Beijing during this particular period. And that trend is continuing every year. So if you compare the concentration in 2020 during the lockdown period with the same period in 2019, you're double counting. You're looking at some natural trend in here. Again, this is showing in the nitrogen dioxide here. So in the UK, in roadside, you can see those continuous decrease in NO2. So whether you're going to have a lockdown or not, this trend is there. So what we see here in for example, in a previous figure that shows in the BBC News, you can see here is that you can see there. So within those differences between this two lines here, partially this is attributable to this lateral decreasing trend. So under the business as usual conditions, this is you are having a reduced concentration of NO2 during the lockdown period, even if that no lockdown has been in place. So this is why we think we really have to detrend the observational data. Just to say that we have indeed tried to use the similar methodology as proposed by Stuart to build the model and predict the concentrations during the lockdown period. we tested this methodology in the previous years, and the performance of that model isn't as good as what we wished for. So this is why we didn't choose that particular methodology. We have been using this detrending methodology instead. I'll explain that how that works. So assuming that we have this is the lockdown date. Let's see, this is the concentration pre-lockdown. This is the pre-lockdown, that's the date. Let's say this is the concentration of NO2 in 2016 to 2019. And, because of the lateral changes of concentration from the winter to the spring, we can see that the NO2 is going down. And this is the concentration after the lockdown. So there is a lateral change here, which is what we call the lateral trend. Now, in reality, we see a much bigger differences. Actually, the actual concentration is lower because year by year, the concentration of NO2 reduces. But the absolute changes in the concentration in 2020 is much bigger. And that is because you have this lockdown effect. And the difference between those, under business as a usual trend, this is what we predict the concentration, or what we call, the predicted concentration. And the difference is here. This is the real difference that we can attribute that to the lockdown effect. And this is what we did. Now, if we do that, this is what we see. I'm not going to go to, every single city. Let's just look at the Wuhan city. Okay, so we can see those NO2 reduced by 47%, by the observed concentration reduced by nearly 50%. And if we detrend, remove the trend, we are seeing a 34% decreases. Now, if we look at the ozone increased by 166%, but if we detrend that, we only see a 22% increase. So there's a huge impact of the trend that affect our analysis. And by detrend that, we are providing something we would call a causal effect. That's something that you can attribute to the lockdown effect itself. Now, there are some further complications because in China, for example, the lockdown date is exactly the date of the Spring Festival, where there is, national holiday. And we modified the code and included this effect in our model, which then, enable us to calculate the real effect that's attributed to the lockdown. So we can peel off the holiday effect. We can look at the real impact due to the lockdown. And looking at this impact in another megacity, look at different periods of pre-COVID lockdown. This is the Spring Festival period, and this is the Spring Festival, and the 1 week after Spring Festival, it's kind of usually it should have gone up to the similar pre-COVID level, but it was because of a lockdown. You're seeing lower levels. And basically, we're seeing a similar trend here where the concentration of PM10 goes down, due to the Spring Festival effect, and the PM 2.5 goes down, and the CO goes down. And it's generally the similar result I was showing here. Now, the difference here is that the SO2, we didn't change that much. The NOx, I can't get rid of this. Anyway, the nitrogen dioxide reduced by a much bigger degree than the other pollutants. We can also see the response of aerosol chemistry. Just look at the, for example, look at the NO3 to nitrate to sulfate in fine particles. What we can see here is during the lockdown effect and during the Spring Festival, this is both are somewhat associated with the lockdown. We can see a much decrease in the nitrate to sulfate ratio. This is understandable because there isn't much change in SO2 because it mostly comes from industry and power plant, but there is a huge decrease in NOx levels because of the traffic, reduced traffic flow. So NOx goes down and the nitrate to sulfate ratio goes down. This is reflected in the composition as well. And we can see the sulfate to EC goes up during this period because of a lot of the EC elemental carbon in the cities comes from the road traffic, for example, and the road traffic is being cut by but the SO4 didn't because of the sulfur dioxide didn't change much. And we can also see the changes in the sulfate conversion rate, essentially the ratio of sulfur sulfate to the sulfate plus SO2. And you can see those goes up during the lockdown period, and the nitrogen conversion rate also goes up during the lockdown period. So in summary, we do see a abrupt drop in NO2 levels in all the cities, but overall not as big as we thought when we detrend the result. And we see the increase in ozone, and we didn't see much changes in OX. And that, the increase in ozone is largely due to the photochemical state rather than large change in the oxidation chemistry. We have seen the PM2.5 decrease in all cities except London and Paris, but we didn't see the abrupt change except in Wuhan and Rome. The point we're really making here is, by combining the deweathering and the detrend, we are able to quantify the real causal effect of the short-term emission interventions on air quality. This is not only for lockdown, it could be applied in other kind of conditions, such as the introduction of low emission zone, etc. And that's all. Thank you very much for your attention. Any questions?
Thank you, Zongbo. Do we have questions? Maybe I could ask the first one. Your random forest model seemed to include variables like Unix date in the variables used for prediction. Can you say a little bit more about that?
It's important to include that because if you think about the trend we're predicting in the model is in a different time of the year, the emissions is different, and including that, you're able to essentially taking those trends into account. That's it's built-in the model. I mean, Tongbo and Stewart will be the expert. I didn't actually do the modeling myself, so I
Thank you. Great. So we have a question from Robin Lambole. How confident are you in the sign of the detrended PM2.5 increase or decrease?
What's the question? It's how, where is the question?
How confident are you in the sign of
the
the
sign is,
detrended
we're very confident with
PM2.5 delta?
the sign, with the actual, the actual quantity, the percentage change, that would be more difficult. The NO2 is relatively straightforward, a lot like the PM2.5, because it's a secondary and it takes time to see the chemistry effect, and because the PM2.5 in the big cities, they are primarily secondary. There's very little from the primary sources. what that means is that, you know, even if you see, you know, reduced traffic, you're not seeing a big changes in the PM2.5 concentrations. So there are complexities in those. What we did is, you know, we including those back trajectories, we including, you know, many other parameters that could potentially affect the PM2.5. That gives us more confidence in the deweathering process. What we have confidence is if there is a pollution event comes from our peculiar area, which is the model didn't see before, and the model didn't understand that. So the model it's not able to learn from it. And that is the case where you will have potential uncertainties. But overall, we are able to estimate uncertainty as well in our model. So in all of the reported results, we not only report the percentage change, but also the uncertainty.
We have another question from Ben Drummond. Which MET variables did the random forest method pick up?
I can't remember that
PM
now. I need to go to look it up. I think in our 2019 papers, we'll have looked at that quite specifically. I would be happy to answer the questions if you drop me an email.
Great. There are no more questions, so I'd like to thank you, Zongbo, for your extremely wide-ranging presentation, and ask Hartmut Bersch to take the stage, please. Yeah, we can see your slides, Hartmut.
Yeah, can you hear me? Oh, but you can't hear me?
I can see you.
Okay, very good.
And now
so
I can hear you.
Thank you very much
Great.
for the invitation. So I would like to present here a study we did on the impact of COVID lockdown, on specifically focusing on the UK, but also with a big focus on how we can really make use of satellite data. And this is really a study that has involved a good number of people across the UK. I want to specifically highlight the contribution of Dan Potts, who actually also was the lead author on a paper about this topic, but also Eloise Marais and Richard Pope, who have been very instrumental to this study. Well, luckily, we already heard a lot about, of course, the impact of COVID, and I don't really need to introduce the topic very much. Of course, as you already heard from Zongbo, coronavirus was, of course, first reported in China, where it had the very big implications. But of course, it had been declared a global pandemic, and we had almost all countries in the world have now been impacted by COVID. As a consequence, we have seen various levels of lockdown and curfews restricting essentially travel and movement of people, which has of course led to significant reductions in traffic and also associated emissions of pollutions from traffic. And this is of course what we are interested in really examining the impact of this very strong perturbation on air pollution across the UK. Now, we are of course fortunate now that we are really in an epoch where we also have fantastic new satellite data. So this is something we couldn't do 10 years ago. So I think this study here heavily relies on a relatively new satellite data with a new satellite mission, which is called DROP-OMI, or Sentinel-5 precursor. So this is essentially the first dedicated atmospheric mission of the European Copernicus program. And the key focus of this mission is really to give us this very easily accessible global data sets of a whole wide range of species. And of course, the primary species we are interested in is NO2. So essentially with DROP-OMI, we can get global data sets with, for a satellite, quite good spatial resolution, which is 5.5 by 3.5 kilometers square. So this is very good, but of course, it's still relatively coarse if you're interested specifically on cities. So, but it gives you the big advantage. Essentially, with a satellite, you can see the whole world every day, and you can, of course, really see the whole larger context. And of course, I just want to first quickly show one of the kind of primary examples, and this has been really at the beginning of the COVID pandemic. Essentially, we have seen many examples where people have used satellite data sets specifically to look at China and other areas. And I want to quickly show an example here as well, which was a study we also did in response to a request by DEFRA. Essentially, China had decided to have a lockdown, of course, very early on, essentially in January, which was then gradually relaxed. And what we see here are simply some satellite images, where the first one is a time period around mid-February, which is essentially before the lockdown. Sorry, these are swapped. Sorry, the first one is mid-December. Sorry for that, which is before the lockdown, where we can, of course, see this massive pollution hotspot over eastern China, where we have a very large number of mega cities. And then if we go to mid-February, where we had the lockdown measures, we have this very large drop, which is really very significant, which then, if we move towards end of March, beginning of April, we can see that numbers are going up again. But of course, it's much more interesting to look at this from a time series perspective. And what we have here is essentially the time series on the left, and you can see that, of course, before the lockdown, we get some artifacts when the data coverage is coarse. So this is the red line, is essentially a 10-day average. And if we move towards the end of January, we had essentially the lockdown. But of course, as already mentioned by Songbo, this is also, of course, exactly the date of the new year, which is a big problem because, of course, you can't disentangle so easily the two effects. So we see this very significant drop and then a gradual increase again towards the expected levels at this time of the year. And just to get a kind of a reference data set, we can now compare this against the 2019 data set. And here, this data set is now the 2019 time series is shifted to reflect essentially the slightly different day of the new year. And as you can see, of course, in both years, 2019, 2020, we can observe this significant drop with the new year. In normal years, 2019, this then goes back to the expected trend. And of course, now we can see the difference in 2020, where we essentially a difference here of around 50%, where values are much lower than what they should be. Okay, but in this talk, I really want to primarily focus on the UK. And as I already mentioned, the UK is relatively complicated. So we had the lockdown was announced relatively late compared to other European countries. So to put an exact date on it is actually not so easy. So we use essentially the 23rd of March, but I think it was only put in law on the 26th of March. And then essentially we had a gradual reopening of the country, starting from 10th of May, but extending all the way into the June time period. And of course, this is well reflected in traffic data. Here I can show the London traffic data, where you see this really steep drop of traffic, and this is for London, and then the gradual increase. Of course, in the UK, we had 2 more lockdowns. There was a second lockdown in end of October, which only lasted for about 4 years. But again, you can see this nicely reflected in the in the traffic data for London. And then there's the third lockdown, which started just after New Year and beginning of January. And it's a little bit unclear when this lockdown was really lifted. So it was roughly lifted end of February. So you can see this gradual increase in traffic again. And of course, now we can see what can we really observe with satellite data. And so what we have here is really only a monthly mean picture of satellite data for the UK. On the top row, we have data for 2019, and in the bottom row for 2020. And this is really only the first half, so it covers the time period January to June. And of course, what we can see is that satellites very nicely can pinpoint to all the major emission hotspots, all the major cities. And of course, we can see the expected decrease in NO2 throughout the year simply due to photochemistry. Now, if we compare this to 2020, the first thing we can observe is that 2020 has already much lower NO2 values already before the lockdown. So January and February shows NO2 values which are much lower, and this has already been reported by many other studies and has also been mentioned by the previous speakers. So this, we think, is due to unusually high winds and stormy conditions in January, February in 2020, which has led to this very low NO2 values at this period before the lockdown. And of course, it already pinpoints towards the need to really take into consideration weather and transport when considering NO2 over NO2 changes. Now, if we now look at the time period essentially in the lockdown, so here we can see we can probably use April as kind of a peak lockdown period. And what we can see, of course, values of NO2 are much reduced. So we find compared to 2019, we have a decrease in NO2 somewhere between 20 and 40%, depending on where you look. The strongest decreases are typically observed within cities. Okay, and it's quite interesting. So there have been other studies, for example, the study by James Lee. So they, for example, observed a decrease of 42%, which has been derived primarily from surface data. So typically, this means that what we observe from satellites is quite similar, but we actually observe somewhat lower values, which might be due to the fact that we really take into account the whole country, and whereas surface data is, of course, very much centered over cities. So what I also want to point out on the bottom right, you can see essentially different regions, and this is essentially our focus regions for the study that we carry out. So we have essentially 5 different regions. So this is Scotland, Northwest, Northeast, Southwest, and Southeast. And then we have 2 city regions, one reflecting Manchester and the other reflecting London. So I will use essentially these regions throughout the study. Okay, and because there have been several studies carried out using surface data, so we decided first to carry out a comparison between satellite and surface data. And of course, this is a comparison which is a little bit an apples and orange comparison, because we compare 2 very different quantities. So these comparisons we did over London and over Manchester. And you can see that essentially we compare surface NO2 given in micrograms per meter cube to the column measurements by satellites, which is given by the black dots. Okay, and what we really wanted to see is if we can observe with satellites essentially similar variability as is observed with surface data. And this surface data is averaged over the cities, and we use 8 different stations over London and I think 3 different stations over Manchester. And we can essentially observe 2 things: that first of all, especially in winter months, January, February, satellite data tends to be very coarse because the UK is very cloudy. So this means that the data quality is somewhat poorer, but also especially this is observable primarily over Manchester. The agreement is somewhat worse, which we think is due to the reduced surface sensitivity of satellite data due to the very shallow boundary layer. However, if we move towards more the spring and early summer months, which is the time period also of the lockdown, we actually find a really very good variability where we can see in both data sets very similar day-to-day changes, and of course differences between weekday and weekends. And we typically find correlation coefficients of about 0.7, 0.8, which I think is quite satisfying for these kind of comparisons. Okay, so we already heard that it's very fundamental to take into account weather effects, but also to take into account the already normal expected trends in trace gas emissions. So in contrast to previous speakers, we are not attempting to do this with a machine learning approach, whereas in our approach, essentially we use a chemical transport model. So we use the GeoSchem 3D chemical transport model, which was run with relatively high resolution over Europe, 0.25 degree by 0.3125 degree, using over the UK the NAEA emission inventory. For boundary conditions, we use a global, much coarser run, which has been run on a 4 by 5 degrees grid. So with this model, we now carry out multiple model scenarios. So we use a business as usual scenario, which is essentially built in the standard emission inventories and also the expected trend going from 2019 to 2020. And this is what we can then use essentially as our reference. In addition to that, we carried out multiple runs where we have reduced emissions during the 2020 lockdown period. So we carried out runs for a reduced emission of 15, 30, 45, and 60% reductions. And these runs are then labeled as GC 15, 30, 45, and 60. Of course, the UK also had its lockdown about a week later than over Europe. So we first reduced emissions over Europe, and then subsequently we reduced emissions over the UK. Okay, so this is essentially the reference that we use then for kind of testing our satellite data against. Okay, and the way we do that is kind of shown in the next slide. So essentially, we want to use now the GeoScam model to determine contributions of emission changes to the observed 2019 to 2020 changes observed by DropOmi. Okay, so the very first thing we need to do is we need to test how well does the model compare to DropOmi for 2019, which is our reference here. Okay, and this is shown in the, sorry, this is a little bit of a complicated graph. So this is shown in the top graph. So on the left-hand side as a time series, the GeoScam model in red, DropOmi in black. But more interesting is the correlation plot. So what we can see is essentially that there is even over normal conditions. So this means in our reference year 2019, we can see that essentially the GeoScam model tends to underestimate DropOmi. So essentially, this shows that it's quite important to really calibrate these model calculations using normal conditions, because models just tend not to perfectly reproduce satellite data. And here we think this underestimation of the GeoScam model is due to a typical underestimation of these models in the free troposphere. So essentially, we now assume that essentially this underestimation of the model against DropOmi data is very systematic, and we would expect that the same underestimation is observed for any other years, also including 2020. Okay, so what we now can do is we now compare essentially the same model run for 2020 with our different emission scenarios. Okay, and in the second row, we see the business as usual scenarios. This is if there is no emission reduction. And what we can observe now is that now the model essentially overestimates by about 20% what we should observe according to our calibration from 2019. Okay, if we want to bring the model satellite comparison, essentially we want to get a consistent comparison to our reference year 2019. This means we need to look at one of the reduced emission scenarios, and we find that typically a scenario of about 30% gives us the best match. Okay, and we now can also assume that between our different grid points, between the different model runs for 15, 30, 45, and 60%, we can roughly linearly interpolate in between to estimate essentially which of our emission scenarios gives us the best match, the most consistent match between GeoScam and DropOmi for the lockdown period. And what we then find is essentially that for our city regions, London and Manchester, we need a emission reduction of about 40% for London and 30% for Manchester, whereas for our larger regions over the UK, we have emission reductions consistent with the satellite data of about 20%. But for some regions like the Northeast and also Scotland, we cannot detect any noticeable changes from satellite data, because these areas are simply have not enough big major NO2 pollution hotspots, so that they are not enough impacted by these emission reduction scenarios. We can of course also now consider how does this play out on as a spatial distribution. So this is shown here. Okay, on the top left panel, we simply see the model GeoScam differences for 2019. This means for the reference, which is then followed for the 2020 business as usual scenario. And the value of M here gives again the regression. So what we can see again, that the business as usual scenarios leads to an overestimate of our 2019 calibration run. And to get consistent results, we need to look at some of the reduced emission scenarios. And what we find is that on a national average, we find the best agreement roughly for an NOx emission reduction of about 20%. Okay, so we also now essentially repeated the same exercise, but using a slightly different metrics. And here now we are considering simply directly the relative change between 2020 and 2019. And we compare we now want to find where does the observed change between TROPOMI gives us the best match with the different geoschem model runs. So this is essentially looking almost at the same, repeating the same exercise, but using a slightly different metrics. In the first metrics, we used essentially a linear regression using a robust regression method, whereas here we are directly looking at the median difference, which is potentially a little bit more sensitive to outliers, but we still want to have the second method to see if we get very similar results. And the first thing we can observe is for our different regions, which are labeled here, Southwest, Southeast, and so on, and then the London and Manchester regions, we can see that the change in NO2 between 2020 and 2019 shown observed by TROPOMI ranges between 6%, which is almost nothing for the Northeast region, all the way up to 40% if we look at our major pollution hotspot, London. What is also quite interesting here is essentially if we look at the change between 2020 and 2019 for the business as usual scenario, this essentially gives us a way of quantifying the changes simply due to meteorology between different weather conditions between the 2 years, and also the expected emission changes which are built into our business as usual change. So what we can see essentially that this impact ranges all the way from about 9%, actually plus 9%, to minus 23% for Scotland. Okay, you can see that if you compare the black bar, which is the observed TROPOMI data, and compare it to the business as usual bar, you can see that there are some regions like the Northeast, essentially where almost all of the observed change in TROPOMI can be explained essentially effectively with the business as usual scenario. Okay, but of course, if we now look at the areas where we can observe much stronger reduction in TROPOMI, we can now again use this comparison to estimate the required emission reduction to bring the TROPOMI difference in agreement with the modeled geoschem difference. And again, what we observe is we find very similar values as we found with our first method. For London, we find that we can estimate this emission reduction to be about 45%, 46% for London. We find a somewhat lower value for Manchester, again of about 20%. And for our different regions, these values varies between 15 to 30%. And again, we cannot observe any noticeable reduction for the Northeast and for the Scotland region. Here all the observed changes can be fully explained with the business as usual scenario already. Okay, so this is nice. So this means that we have now established that we can essentially estimate the overall emission impact or the emission reduction so that we can get consistent results between our geoschem model run and what we observe with satellite data. So we can now use this as information to really kind of try to model and establish the timeline of the emission reduction or of the impact of emission reduction on observed NO2. And this is shown in this figure here. So this is focused on London, and for London we have used here an emission reduction of about 45%. Okay, so the different curves here is in black. We have the normal reference year 2019, and we have two different curves for 2020. In red is the business as usual model run, and in blue is the model run with a 45% reduction in emissions. Okay, and we have essentially 2 points that we need to consider here. The first point is the lockdown in Europe, which is then followed by the lockdown in the UK. Okay, and in the top row, we have essentially the column NO2, and in the bottom, we have the surface NO2. And again, as we already observed, what we can see is there is a significant difference between before the lockdown period between the year 2019 and the year 2020, which is primarily due to different weather conditions between the 2 years. Okay, but what is also quite interesting, if we compare after the lockdown, the impact on the emission reduction on columns and on surface, we can actually see that the 45% reduction in emissions has a very similar impact on the column observation. In both cases, the column and the surface is both reduced by slightly more than 42%. And this is important because this really illustrates the high sensitivity of column observations over these city areas to local changes. So essentially, column observations provide a very similar piece of information over cities than surface informations. We can also see another quite interesting effect. Okay, this is if we look at the impact of the reduction in Europe, we can actually see that our two model runs, the business as usual and the 45% reduction model run, they already diverged before we have the UK lockdown. So this really shows the influence also of long-range transport towards the UK. So where we have also an influence of the earlier lockdown over the mainland Europe on what we observe in Europe. And I think this is also an important contribution that needs to be taken into consideration. Okay, now because we have now established essentially our global model run, we can now use this model data also to have a look at the impact on surface ozone and PM, which is all driven by what we have observed by the NO2 reduction. So here we are using a model run that represents our determined global average emission reduction, which has been estimated to be about 20%. Okay, and what we show here is essentially model simulations for 2019 compared to 2020, where we allow the 20% emission reduction. Okay, in the top panel, we have the model simulations for surface ozone, and in the bottom row for PM. Okay, and what we can first of all observe that on the left panel, we have the 2019 data, where we have very, very low ozone values around cities, with values lower than 30 ppb. And we also find quite good consistency between surface data, which are the circles. All the little circles are different surface stations from the ORN network. And we find overall quite good agreement between essentially the geoschem model run and these surface data, which gives us, of course, confidence in our model data set. Now, if we move towards 2020, we can see there is a substantial increase in surface ozone to values ranging from 32 to 35 ppb. However, we do see that there is less consistency within cities, and this is not very surprising because we know that this nationwide reduction of 20% is, of course, an underestimate for what happens in cities. So for cities itself, we know that there is a much larger emission reduction, which is much more with a value of 45%. Okay, and so this what we really see here is simply that over cities, of course, we would have to apply a much larger reduction to get consistency with these surface measurements. Okay. All right, I'm hurrying up.
2 minutes.
So here we have now, so now we can of course also look at PM. So PM, of course, is much less heterogeneous than ozone. It's much longer lived. Again, we can observe that in 2019, we get quite good agreement between the model and what we observe with surface stations. We also get quite a good agreement in the decline between 2020 and 2019, which is about 3 microgram per meter cube. But again, what we observe is that the model tends to underestimate significantly what surface sensors observe in cities, and this could have many reasons. For example, the coarse resolution of the model does not represent cities very well, but of course there are also other precursors that have not been reduced. Okay, finally, most interesting, so this is now the effect of the 20% emission reduction on ozone and on PM. So this is the effect of this national increase. So on the left-hand side for ozone and the right-hand side for PM. So what we can observe is that nationwide, the impact on ozone is very small, but we can see this significant difference between cities and rural areas where we see an increase, as you would expect, over cities, which is modeled to be about 1 part per billion, and the decline over more rural urban areas. Again, if you assume that the emission reduction over cities is much larger, we would about 45%, we would actually find an impact on ozone of about 2 parts per billion. Now, the national decrease in PM 2.5 is about 1.1. And quite interestingly, we see the largest response in the southwest, which we attribute again primarily to transport of reduced primary and secondary sources further upwind. Okay, before I come to my conclusion, I just thought I'd also give a quick view on what actually does happen in the other lockdown periods. And this is essentially an overview over what we see with satellites for the 3 different lockdown periods. So the top one is the lockdown period 1, which I already discussed, which is followed by the very short lockdown period 2 and the later lockdown period 3. And I think what is quite interesting that in all 3 lockdown periods, we can observe with satellites a significant reduction in NO2 compared to 2019. But of course, for all of the different lockdown periods, weather will have an important role, and which has not been investigated here in this very quick illustrations. Okay, and with this, I want to essentially come to my conclusion. So what we did in this study, we examined this dramatic drop in air pollution due to lockdown measures in the UK, and we did this with a detailed model and satellite analysis. We estimated that emissions UK-wide dropped by about 20%, but this value is much higher over cities, especially over London, but it's really marginal over areas like Scotland. We do show that meteorology and long-range transports plays an important role explaining the differences between 2020 and 2019, and we think this can explain about half of the observed changes. So what this really shows us is that we really need to consider emission changes, but also meteorology and pollution transport, long-range transport pollution in our efforts towards designing air pollution mitigation measures, and also when we want to enforce these policy standards. If you're interested, so essentially all of this is published in this publication earlier this year, which came out in Environmental Research Letters. Okay, thank you very much.
I think for the purposes of keeping to time and finishing on time, I'm going to ask you to answer the questions in the chat. They're mostly about attribution of sector-based emissions changes, which might be a challenge for your data. But if Robin is ready, I'd like to ask him to take the stage and to present. Anyway, thank you, Hartmut. Very thorough and interesting.
All right, hopefully you can all hear me. Good. So I'm going to talk to you about CovidMIP, a model into comparison project using near real-time emissions data, trying to update some projections for what COVID means for climate change. There are actually too many co-authors to fit on a single slide. I will just say that Chris Jones was very, really the driving force behind the project. So I'm going to investigate why you might want to track real-time emissions, how you do it, what these imply about the effects of COVID-19 for climate change, and whether or not we can trust them. So as we've heard from a lot of people, there's been this huge drop in emissions during lockdown. But if you want to put this into climate models, you need to have gridded emissions data for all countries in the world. Authoritative country level data often lags by 2 years or more, depending on the country. And gridded data is typically more than 5 years out of date, simply because it's very hard to attribute exactly where emissions are coming from. So the question is, can we quickly assess whether old climate change projections need correcting? This was particularly motivated by the fact that AR6, so this big report, has been coming out over this year and will continue coming out next year, different working group sections of it. And we essentially want to know whether all of the projections in this need correcting for the effect of COVID-19. So has COVID-19 helped us reach our climate targets? Can we still trust any climate projections before COVID-19 in the long run? And in the short run, the questions that we have interest in are, do we see changes in expected weather patterns for just the years where we see lockdown? And do they have a significant impact on health? Although that it won't be the focus of this talk here. So you might think we could just use an existing low emission scenario. There are quite a few problems with this. So firstly, because as I said, emissions data is usually 5 years out of date, they actually all start diverging, usually in 2010, 2015 in the best case, so before COVID starts. Usually they're gridded on decadal or 5-year periods. So if you change the year in which COVID happens, you'll effectively see a precursor to that and a postcursor to that. So it affects the years around it as well. And the changes are expected to be long-term. Whereas what we want to model is what happens if you have a sudden fall and presumed rapid recovery. So we have seen fairly rapid recovery. At the time that a lot of this work was done, it wasn't clear that we would have a rapid recovery, although most of our model circles around the idea of recovery back to baseline in 2 to 3 years, which turns out to have been a little optimistic, but not hugely pessimistic, depending on how you see recovery versus emissions being important. So we do definitely need new groups of scenarios that accurately represent the effects of COVID-19 itself, and not simply having generally a trend of lower emissions. So how can you create this on a very rapid timescale? We need a lot of groups to run code so that we're sure that the effects we're seeing are not simply the results of quirks of a single model. In order to do this easily, we want to use a baseline case that's already been computed. That means we can use their spin up to a certain point in time. So we don't need to compute all of history. We can just diverge from the baseline in 2020. Also gives us an existing pathway, which is already gridded. So we can just modify the gridded values rather than having to construct a complete worldwide map of where emissions are coming from. We will then update this using our near real-time emissions estimates, which are usually emissions factors, and we can expand this into the farther future using basic economic projections. So the near real-time estimates that we use are mostly based on Google mobility data. We augment this using data from the Lequere et al. Study, which basically consider the degree of lockdown of the different regions. So places like China, for instance, just don't have available Google mobility data. And also we use aviation data that is from Flight Radar 24, just as our main source of data for aviation. So Lequere did produce aviation estimates, but we had, basically we wanted to update these in a different way. So you can see in this paper here, which is from Forster et al., that basically if you use the Lequere estimates, we are emphasizing here the high estimates for reasons that we'll come back to later. But if you compare the high estimates to Google Transit data or Apple driving data, and in some cases also the Liu et al. Data, which is the Carbon Monitor project, but also tried to do much the same thing as this. In their case, largely using sources like TomTom data and a lot of emissions factors from industrial power consumption and things like that. You can see that they are certainly not producing the same value, but there's generally fairly good correlations between them. So yeah, here we have graphs with population-weighted histograms, and in part A, and part B shows the difference between using these different types of data. For aviation, as I say, we took the data from Flight Radar 24, and you can see that there was this huge drop in early 2020, and it has not recovered. It actually still hasn't recovered if you look at the data to now, but it is relatively close to being back to where it was. You can find this data on their website. It's going out for free. So on top of this, we'd like to create some projection into the future, because it's obvious that COVID would continue to have some effects on our economy. So the standard assumption is that you would continue at 2/3 of the most recent level for the end of the 2 years, so until the end of 2021. And then after that, you would return to normal over the course of a year. And we call this scenario the 2-year blip scenario. We made some various variations on these. So one of them was the 4-year blip cycle, which is where you spend 4 years at 2/3 decrease from the most recent data, and then a 1-year return to normal, or a 2-year blip followed by one of 3 different like long-term trends in CO2 emissions. These were based on the Climate Action Tracker's assessment of long-term impacts of COVID-19. So the 3 scenarios that they looked at were increased fossil fuel use if governments devote money to funding more fossil recovery, increased green investment either in a moderate way or in a substantial way. These basically gave us Kyoto totals, and separately I've worked on a program called Silicone, which is designed to take a projected emissions basket like the Kyoto gas total and break it down into components that you can use to actually run your climate models, because governments usually are most accurate or most focused on reporting Kyoto gas totals, but those are not particularly useful if you want to actually put this into a climate model. So what this does basically is we use our scenarios that we've projected using the estimated Kyoto totals, considering the effects of investment resulting from recovery. And we can see how this scenario would decompose using previously existing scenarios from the SSP2 message globium model series. So here you can see that the continuous lines are all of these existing scenarios. And we have got these dashed lines that are our new models. You'll see that one of them, the strong green recovery, is greener than anything that previously existed. So we can't use this set of scenarios. So for that scenario, we had to use the SSP1 message globium scenario set. Essentially just a slightly higher effort group of scenarios. But these are technical details you can find in the paper if you're interested in that sort of side of the project. So we have, from the near real-time emissions data, we have emissions changes based on country and sector. And there are 7 different sectors reported. So we can take this and we have previously existing SSP2 4.5 scenario from message globium, which we chose because it is the closest trajectory to the recent emissions totals and also closest to the NDCs that governments have agreed to. So we took these sets of scenarios and modified them by the relative emissions that we expect. And here you can see some grids for April 2020. Of course, we have this data for a set of years, and the set of years is higher than in the baseline data. So we also had to interpolate years so as to ensure that our blip was a blip that only lasted for the years we expected it to, because natively programs expect things to simply interpolate between selected years. We also produce greenhouse gas emissions. So these are hemispherically averaged expected values. We run the emissions that we got through a simple climate model to get concentrations from the emissions, because a lot of the global circulation models that we are using don't actually directly work with the emissions, they work with concentrations. Although we did also have the emissions data available for those who want it. You'll notice immediately that the 2-year blip is very difficult to distinguish from the baseline, and this should give you a good indication of the results that we're going to expect from the impact of lockdown, i.e. not very much. We also produce ozone concentrations for models which use it. Quite a few models do require ozone to be prescribed, so we generated that for those models. Aerosols are something that many models will generate for themselves, given the different emissions. So we produce emission for the full range of variables. We don't break down non-methane volatile organic compounds, but we do have at least basket emissions for all of the major emissions types. However, some models actually just want aerosol optical density, so this is like total aerosol load. So we have one group that produced this data, which all groups could use if they need. So 12 different simulation groups around this model. I believe it's actually now 13, but one of them came in relatively recently and we haven't finished processing their data. With different resolutions and different numbers of scenarios in the ensemble. And the results of this were compared. And what you see is that there are limited and short-term impacts from our 2-year blip. So all of these are comparing the 2-year blip to the baseline case, which is the 0 line there. So in most cases, you see that global aerosol optical density is reduced for the first 2 years. Clearly, returns to baseline, over 2022, and thereafter is about normal, which is what you expect because this emission scenario says we return to normal in 2023, and aerosols don't stick around for tremendously long. So when emissions go back to normal, you very much expect the aerosol optical density to go back to normal. You do see as a result of this that surface downwards shortwave radiation is increased. So it's a situation where you'd sort of vaguely expect there to be higher surface temperature because you've got more downwards radiation. However, actually looking at the temperature, you don't particularly see any trend. Essentially, annual variability and other factors simply swamp any effect that you might see. You also don't really see any change in global precipitation. So any effects that you might see here are simply swamped by normal variation. Looking a little bit at the gridded data, so all of the models produce different data like this. So this is the aerosol response that we saw previously was significant in aggregate. We can now see a breakdown of it over regions. And we see that in many cases, the strongest impact is found over South and East Asia. So we then looked a little bit more carefully at the data there. And we see that, again, aerosol optical density substantially change, surface downwards radiation substantially change. Now, here we also do see that surface air temperature is substantially changed. In all models, you see that the 2020 values are above what you would expect in baseline. Now, precipitation in the aggregate does not seem to particularly change here. It is worth noting that several individual models, and indeed a publication based on one of the individual models, do see individual effects that indicate enhanced monsoon effects. It's also possibly worth noting that historically there were very high levels of monsoon in 2020 and 2021. So we are going to continue investigating this to see if there are regional effects, but from the aggregate of all of the models, there is no obvious and strong effect. In terms of long-term effects, we have got some of the models returning these. These were regarded as a lower priority than the short-term values. On the whole, however, they're just not telling a different story to what you'd get if you simply put the emissions into a basic climate model. The baseline emissions are almost identical to the 2-year blip in terms of expected temperature. Fossil fuel recovery is slightly higher. Moderate green and strong green are somewhat lower in temperature. As you would expect, we're reducing emissions. However, it does take a while for this effect to feed through. So the final point to consider here is how reliable this data is. This data was collected under a strong time pressure, so we were very excited to show near real-time emissions. It's just worth taking a bit of time to reflect what that actually means if you want to use this for reasons other than rapidly setting up a model into comparison project. So there's now a reasonable amount of evidence that the Google activity data overestimates the actual reduction in other ways of measuring activity after the first lockdown. It seems that there's some change in human behavior, which just means it's no longer that well calibrated. So one of the results of this is that our estimate of CO2 change was 13%, whereas the aggregate of other means of estimating this were more like 7%. So we expect that our results were an overestimate. You will remember that we specifically chose to use the higher end of the Lequere et al. Estimates, which is one of the results that feed into that 7% number. So we are very much expecting this to be the case, but it's worth emphasizing that this is the case. The advantage of this is that if there were to be an effect, we will be more likely to have detected it. So when we say here that we really don't see any effect at all on the long-term trends of COVID for the 2-year blip, we can have quite high confidence that this is the genuine finding. Obviously, it gives us less confidence in saying that the higher emission reduction scenarios genuinely didn't see an emission reduction. On this plot, you can also see that we are specifically calling out, well, so it's not us, sorry, this is data from the ODA paper showing that the Google data, which is the line in purple, is the most overestimating of the actual use of fuel in Japan over this time period. So the blue line with little error bars on it, that's the fuel-based, which is considered the best estimate, and the Google data is essentially overestimating the change by the most. And there's further evidence this is an overestimate because you see here from Spain that even if Google is relatively accurately depicting the total change in traffic, it is very much overestimating the change in the use of heavy-duty vehicles. So essentially, all the trucks have to keep going, even if the individual cars are more like to stop. Well, that's going to substantially increase the actual pollution because they're more polluting than the smaller cars. So in conclusion, we see short-term impacts of lockdown, but this is primarily on aerosol levels, and there are only small and regional temperature changes. We don't really see significant long-term impacts from the lockdown itself. The long-term changes from investment or governments taking action to ensure there is a green recovery are substantial, but not the actual lockdown itself. On the one hand, we would like to put more effort into seeing whether these investment changes do change weather patterns and other regional effects like that, and also more effort into seeing regional changes on monsoon behavior, but it's not large and obvious so far. The general conclusion that you can take away from this, however, is that pre-COVID-19 climate projections are still largely correct and applicable. We have data for those of you who actually work in this field and are wanting to take part in this model and comparison project available here. All right, thank you for your time.
We have a question from David Stevenson. Did you estimate methane emissions changes associated with COVID?
We did.
In your work?
I don't know if you want me to go into any details about how we estimated them, but essentially all of the Google mobility data gives you sectoral information, and we essentially just said if you're reducing the activity of this sector in this country by a set amount, then you would expect the methane to go down in proportion to that. So it's not a very detailed model, but yes, we definitely produce a complete set of emissions data.
There's a comment from Zongbo. We saw much smaller effects on NO2 than we originally thought. We thought that most polluting vehicles such as HGVs and LGVs.
Yeah, I think a lot of us were sort of caught out by the fact that you can see a reduction in some forms of traffic, but actually when you start looking at breaking down the types of traffic, you would just expect to see less effect.
Regarding the experiment design, I noticed you used a huge number of ensemble members in the experiments. Would there have been any advantage in using a slightly different approach, say a time slice-based approach that might drive down the statistics a bit?
One of the very powerful techniques that we encourage people to use, but most models simply are unable to, is this sort of nudged thing, because we're essentially looking for small changes. So for most of the models, unfortunately, you do just have to run it a lot of times with slightly different initial conditions. Some models allow you to actually just analyze the effect of a small delta. So the although it's not included in this talk, Andrew Catalman has done quite a lot of work on this, and I can give you links to a paper of his where he did basically take this data for just the 1 year, and you can see an effect more clearly in that than if you're doing complete climate models. But because we are looking for quite small effects, you do just need large statistics to pick them out from the noise otherwise.
Yeah, and for temperature and precipitation responses, you need sort of coupled models, don't you? Great. Okay. I see no more questions in the chat, so I will conclude this session by thanking all our speakers and the audience for their questions. We'll begin again at 2 o'clock.
So, hi everybody. Welcome back after the break. Thanks to the speakers again for this morning's session, and we're excited to hear what the speakers this afternoon have to say. So it's 2 o'clock, so we'll make a prompt start. So I'm delighted to welcome to the stage then David Stevenson from
thanks very much
University of Edinburgh.
Brian and
over
Paul
to you, David. Thank you.
Inviting me to this meeting to talk about this stuff. So I want to talk about methane and how the lockdowns possibly affected methane. So I've got this slightly provocative title, perhaps, that I think we can explain much of the increase we've seen in methane with and relating it to changes in NOx emissions. And this is, there is a discussion paper about this. It hasn't been accepted, as you will see if you look at the reviews, but there's a discussion paper on ACP with some reviews and some responses about this, if you'd like to see a bit more. It's a very short paper, which is possibly why it's got some slightly stinging reviews. But anyway, I will talk a little bit about this and how we are hoping to revise it. So I should acknowledge that this work is sort of been done in collaboration with Dick Derwent, my old boss at the Met Office, who's still very active working on atmospheric chemistry, Oliver Wilde and Bill Collins, who will be well known to lots of you. Anyway, so one of the things I should say immediately is that I would like to slightly revise the title from being able to explain most of the coincident change to maybe a significant fraction of. I'm not completely backtracking on my suggestion here, but I think possibly my choice of words by explaining most is perhaps a bit too strong language. But anyway, so we've seen these maps already, and actually it's been nicely illustrated that these maps are perhaps a slightly unreliable way of saying how much NOx changed during the lockdowns. So I was going to compare this with this is just comparing January and February. So of course there is the Chinese holiday as well as the lockdown in here and changes in weather. But I think we're all agreed that NOx emissions were reduced quite a lot during the lockdowns. And if we go back 20 years, modelling results from Oliver Wilde from 2001, this paper published, indicated that NOx emissions actually cause global cooling through changes in methane. So essentially, when you emit NOx into the atmosphere, it will increase the amount of OH available and will shorten the methane lifetime. So this was quite nicely quantified by a series of modelling studies, including this one from Oliver. So essentially, when you add the NOx, you increase OH, and it has an immediate impact on methane. And I was quite interested really in working out if the magnitude of the NOx emissions changes that we've seen during lockdown could in any way induce a significant change in methane. So the mechanism, the way this works, again, I'm not going to go into the chemistry in any great detail, but essentially more NOx means more OH because of this reaction, NO plus HO2. So you produce more OH, and of course the main sink for methane is methane plus OH. So you increase the sink. And of course the opposite of this is what happened during lockdown. There was less NOx in the atmosphere, so we would probably expect methane to increase. So really, how much more methane would we expect given the lockdown reductions in NOx emissions? And this idea that NOx reduces methane is I don't think really controversial. It is embedded and well used, well accepted, I would say, by the community. So much so that it features in the IPCC reports. So this is a figure from the technical summary, but essentially it is in the summary for policymakers, the second figure in the summary for policymakers for IPCC. So and really this comes from model studies that show that essentially what I just showed you from Oliver's study, that NOx emissions cause cooling by reducing methane concentrations. Okay, this is over the timescale of pre-industrial to present day, but essentially we can calculate these numbers using models, and although they have large uncertainties associated with them, we think this is a real effect. So this really shouldn't come as a surprise that the NOx reductions from lockdown might induce an increase in methane. So what did happen to methane during lockdown? And maybe this is a surprise to you. I went and looked at the NOAA website to work out what was going on. So interestingly, this is what's happened. So this is taken from the NOAA website. So NOAA operates a network of sites measuring methane and collate this together to produce a global methane value and a methane trend. So the plot on the left here is showing monthly values of the methane mole fraction over the last 5 years. And you can see in 2020, there was a fairly sharp inflection in the growth rate. And we can quantify this if we just take the gradient of this. So again, I'm just using NOAA values here. So the graph on the right has the annual increases over the entire record back to the 1980s. And if you look at the 2020 value, it is larger. It's the largest value in the whole time series. And if you compare it with the year prior, so comparing 2020 with 2019, so the annual growth rate in 2020 was about 15.7 ppb. And in 2019, it was about 9.7 ppb. So there's an observed increase in that growth rate from 2019 to 2020 of about 6 ppb. Now I've put a star next to that because this growth rate that you can extract from the NOAA website has actually changed quite a lot over the last few months. So the paper I wrote for ACP in the summer actually quotes an observed increase of 4.9 ppb. So I was a little bit surprised when I downloaded these data yesterday and got a number that was 6 ppb. So it just goes to show, I suppose, that I'm not quite sure why it changes. I don't know if it's the NOAA algorithm, the way they calculate these numbers, or if new data has actually gone into those 2020 numbers. So I'm going to look into that a bit more closely, but this has slightly spoiled my story, but it doesn't completely change the picture at all. But it was interesting to me, I think, to find out that actually the observations of how much methane has changed are, somewhat uncertain. That really wasn't I thought the most uncertain part of this story was elsewhere, but maybe the observations are quite uncertain as well. Okay, so just to add to that paper by Oliver, so Dick Derwent and others and myself in 2004, there are a series of papers that have essentially done these sorts of experiments where you add a pulse of NOx into your model and you look at what it does to OH and what it does to methane. So this is just another series of experiments similar to the one I just showed you from Oliver. But essentially you can quantify, so these are all been normalized to adding 1 teragram of NO2. In this paper from 2004, I added it in, I did a series of experiments where I added it in different seasons, January, April, July, and October. But essentially you get the same or a rather similar response whenever you add it. You get an instantaneous, essentially, increase in OH, and this takes a chunk out of the methane that's in the atmosphere. So you get a rapid response in methane. You might think that you would actually get a longer term. It would take a while to appear in the methane, but actually it appears instantaneously as the OH changes. You get, or pretty rapidly, you get a big chunk taken out of the methane. there is a long tail associated with how this relaxes after you've added the pulse. But essentially, you can work out the change in methane for a given increase in NOx. And these experiments are actually, I think, really quite similar to what happened during lockdown. We added, I guess they're the opposite. Rather than adding extra NOx, we reduced a significant chunk of NOx. But essentially, the same processes are going on. So I think they're really quite useful for trying to work out what happened with methane. Now, one of the things we were criticised for in the submission was that we weren't using very up-to-date models. So a slightly more up-to-date version of this. So those studies were from 20 years ago. But HTAP, the Hemispheric Transport of Air Pollution Project, have done a series of experiments. And this is actually from the first phase of HTAP recorded by Fry et al. In 2012. So what they did was analyze a series of experiments where, if you're familiar with HTAP, this is going to be a little bit boring, but essentially we reduced emissions in 4 world regions, so North America, Europe, South Asia, and East Asia. And essentially did 20% reductions in NOx emissions from those regions, and then looked at what that did to methane. And similar experiments with 20% reductions in VOCs and CO. Now, there is a slight technicality that I'm not really going to go into, that these experiments were actually step changes, or essentially they weren't pulses like the previous experiments. So, and they also used fixed methane boundary conditions. So the models actually just diagnosed the change in OH and then backed out what would actually have happened, or how methane would have changed given that change in OH and the change in the methane lifetime. So these are a little bit more or less straightforward to actually interpret, but essentially they are equivalent to those pulse experiments. So we have to do a little bit of work to go back and work out changes in methane associated with the changes in NOx in these experiments. But the other useful thing from this HTAP study is that there were 11 models contributing. So we actually have a model spread. We have an estimate of the uncertainty in the sensitivity of methane to these changes in NOx and other species. So we have some estimate of how uncertain these changes actually are. So if we look at these sensitivities, so this is actually just a slightly boring table that compares the numbers between Oliver's study, the Derwent et al., and then this HTAP study. And I'm looking at different world regions, or looking at a global number, a hemispheric number, and then those regions, the HTAP regions. And you can see that the sensitivity of the change in the methane burden to the change in emissions of NOx has some spatial structure to it. So some regions are more sensitive than others. So for example, the Southern Hemisphere is more sensitive than the Northern Hemisphere. We've also done similar experiments with aviation emissions. So we can look at aviation NOx. And aviation NOx is about 5 times as efficient at affecting methane as surface NOx emissions. And really this is just to do with the lifetime of the NOx and how long it lasts in the atmosphere and how efficient it perturbs the OH chemistry. But essentially we can take these regional variations in this sensitivity and we can work out, if we know the emissions changes associated with lockdown, we can work out what we would expect to have changed, how methane would have expected to have changed. So I've used Robin's paper. So it was nice to hear Robin talking earlier before lunch, introducing how we put together those emission scenarios. So essentially I've used those emission scenarios to look at the difference between 2019 and 2020 in terms of the emissions and calculated the changes in emissions associated with lockdown that are estimated from Robin's study. So I'm going to be basically using those emissions together with the sensitivities from those earlier earlier modeling studies to work out the impact on methane. So just to look in a little bit more detail at what those emissions reductions look like globally. So this is a figure taken from the paper, and the NOx is the brown curve on here, which is one of the largest changes. So essentially a peak change of about 25%, I think averaged over the whole year. So I'm going to use an annual change in emissions. Basically, it boils down to 19.4 teragrams of NO2 is what is in this emissions inventory anyway for the change due to lockdown. And we can get a similar number for aviation NOx as well. And that comes out at 0.83 teragrams of NO2. So again, this is about a 25% change, I think, over the whole year. So plugging those numbers in, we can work out the methane change that we would expect for those regional changes in NOx emissions. So here I'm using the HTAP sensitivities in Europe, North America, East Asia, and South Asia. So these are essentially the same numbers that I showed you on a previous table, but now I've translated these into ppb of methane for a teragram of NO2 change. So this is quite crude, but I don't think it's unreasonable. And although there are significant spatial variations that are sort of missed by this sort of back of the envelope kind of calculation, I think we need to remember that actually the HTAP study still had spatial variations within those regions in the emissions. So we're not completely ignoring spatial variations within those boxes. I think the only reason why this method wouldn't work very well is if the variations or the changes during lockdown didn't look like a scaled version of the baseline emissions within each of those regions. And okay, so I think that is a bit of an approximation, but I think it's not a totally unreasonable approximation. Anyway, so if we take those regional sensitivities and the regional changes in emissions, we can basically just calculate how much each region contributed to a change in methane. And if we add those up, we get this number about 3.5 ppb. Now, this is slightly, so we can do this globally as well, and we get a number of 3 ppb. And this is telling you that actually adding the regional information gives you a slightly different number, because you essentially are folding the sensitivities at a regional level rather than just taking a global number. So I think the regional number is more realistic. Obviously, if we had more information from HTAP type studies at a higher regional resolution, we'd be able to do this even more accurately. But I think this is a reasonable approximation. The other useful thing we can get from HTAP is, like I said, there was 11 models, so we can actually get a spread of values for the sensitivities. So if you look at the spread, it's 2.4 to 4.5 ppb. So this is essentially a 1 standard deviation spread of the sensitivities. Similarly, if we can do this for aircraft, and we get about 0.7 ppb ozone coming from the aircraft NOx changes. So the total change from these two is 4.2 ppb. Now, as I pointed out earlier, it's not just NOx that changed during lockdown. So carbon monoxide and VOCs also changed. And these will have had an opposing effect, because as you reduce CO emissions, you actually allow OH to increase in the atmosphere, and that will shorten the methane lifetime. So there is a slightly counteracting effect coming from the reductions in CO and reductions in VOCs. So we can use the same methodology to work out what the numbers associated with these are. And without going into the details so much for this, for CO, I get a calculated value of minus 1.3 ppb. And similarly for VOCs, I get minus 0.7 ppb. So if you add all these together, you get an increase from the NOx reductions of about plus 4.2, plus or minus 1 ppb, minus 1.3 from CO, minus 0.7 from VOCs. So when you add all these together, you get about plus 2.2 increase in methane, which is actually considerably smaller than the observed 6. But actually, if you look at the NOx number, 4.2, this is quite, I would argue that this is a significant number, and this is pretty close to the observed increase. Anyway, so just to summarize, observations show that the global methane jumped from a growth rate jumped from about 10 ppb a year to 16 ppb a year in 2020. And I think this is something to do with the lockdown. You can use model-derived regional sensitivities of methane to NOx, CO, and VOCs, together with the estimates of how much those gases changed, the emissions of those gases changed during lockdown, to estimate an impact on methane. And it suggests that basically the lockdown methane emissions changes can explain quite a significant fraction of the methane change. That is partly counteracted by the CO and the VOC acting in the opposite sense. But I would contend that the NOx changes are a significant driver of those methane increases. I think to go any further with this, I mean, we need to look at the uncertainties, and I think there are uncertainties in what the observations for methane show. I think there are observations in there are uncertainties in the model sensitivities, and there are uncertainties in the emissions changes during lockdown as well. So all of those things will contribute, and I'm not quite sure which ones are the most important to focus on, but they all sort of make a sort of definitive interpretation of what's been going on a bit challenging. But I think if we look at those things in more detail, I think we'll learn quite a lot about methane. Now, I'm not quite sure how much longer I've got. I could stop at this point. Paul or Ryan, tell me if I've got another minute or two.
You have got another couple of minutes, David. Yep.
Okay, I will dig a hole for myself then and talk about the final slide. So I'm not really a fan of geoengineering, but I think this possibly is related, and I think thinking about the methane sink, can we geoengineer the methane sink? And actually, I was surprised by I haven't really been keeping up with the literature, but I did a quick search for this, and actually Olivier and Gerd Folberth were talking about this 10 years ago. So this is a paper from 2010. And actually there's a very recent paper in Phil Trans of the Royal Society about atmospheric methane removal. So it is a sort of an active topic. Interestingly, nobody mentions thinking about using NOx as a way of increasing the methane sink. For very good reasons. We don't really want to be adding extra pollution into the atmosphere. But let me just put this out there as a suggestion. So if we sort of carefully added NOx emissions in carefully selected locations that are really sensitive to NOx, we could change OH. And we could potentially significantly increase the methane sink. So I think this, has lots of ethical problems, as most geoengineering ideas do. But I think potentially, I think these sorts of studies, by looking at what happened during lockdown, hopefully will constrain our understanding of NOx methane OH chemistry, and it would sort of guide whether this is a realistic possibility or not, I think. And I don't really want lots of questions about the geoengineering side of this, because this is just something that I've added at the end. But I'm more interested in actually these conclusions, perhaps. So I'll stop at that point anyway.
David, really interesting talk. So I have a quick question. So is there scope to repeat some of this analysis, perhaps, but with sensitivities derived at a higher spatial resolution? Sometimes, I think you touched on this, but I see the more recent HTAP studies that have included, a very large number of regions, but I'm not sure if they've done these type of sensitivities.
Yeah, no, this is absolutely right. So one of the reviewers to the ACP paper suggested we looked at HTAP2, and I think there probably is useful data in HTAP2, but nobody has analysed it and written it up like the HTAP1 data. So it's a little bit more difficult to get to immediately use. So I'm looking into doing this, but I think it will take me another 6 months or something to actually get anywhere. But yes.
And just to follow up as well, you mentioned the NOAA growth rate and the possible revision to it. Have you looked at the similar quantity but derived from A-gauge data?
I must admit I haven't, no, and I'd be interested to know if there are other ways of doing this. I mean, I'm sure there's also satellite methane data, and I don't really know. I think there is probably interesting information in the regionality and how the methane's changed. I mean, I think we always sort of think about just the global number for methane, but because this is sort of such a short-term impact, I think it probably would be really quite interesting to look at how it evolved over the lockdown months to see if it, really originated in northern mid latitudes and spread out, or yeah. I think the more detailed data on that would be fascinating, to look at.
Great, thanks. So some questions from the chat. One from Paul. Any idea what contribution interannual variability in lightning NOx could be playing?
Yeah, so I think quite a lot of that variability in the methane growth rate is put down or is related to ENSO variability. And I think a lot of the ENSO variability feeds through to a variability in methane through things like changes in convection and where the lightning NOx is. So I think interannual variability in those big natural sources of NOx are a big part of the year-to-year variability in the methane growth rate. Yes, absolutely.
Okay. A question from Zongbo. Did we see NOx emission decreases in the past few years? And if so, how might this have affected the long-term trend in NOx?
I guess maybe you mean the long-term trend in methane. I think this is a really interesting question, and this is partly why I'm doing this, because I think there probably is a lot of useful information you can get out of the lockdown period that will tell us about what's been happening with methane over the longer time period as well. So I haven't done that analysis, but I think if we can learn stuff from lockdown, and if I think we want to know if this mechanism is right, and if it is, then it has implications both for interpreting the last 40 years of the methane record, but also for interpreting how future scenarios for NOx and other emissions will affect methane as well. So I think it really is quite important to understand these sensitivities. And if we've got any observational constraints on what those are, then I think that's really, really useful information.
Okay, brilliant. Thanks a lot, David.
Okay.
Okay, so the next speaker is Ulrich Schumann from the German Aerospace Center. Welcome. Thank you. And I'll hand over to you, Ulrich.
Okay, it suddenly got less loudly, but I hope you hear me. So I talk about the climate impacts of aviation, and in particular on contrail changes, which we investigated for cases over Europe during this recent COVID-19 period. I will start with 2 slides showing the situation with the changes in April 2020. Then I will give a short introductory to contrail formation and climate impact in general, just as a kind of an introduction for those who have not worked on contrails so much in the past. Then I will continue discussing the case study for this one day of COVID day, 16 April 2020, which had a lot of contrails. And then we will extend that for first to 6 months period and then to a 12 months period and compare 2020 with 2019 for 6 and for 12 months and then show some conclusions. Now, yes, next. So this is showing the well-known changes in air traffic which we have observed over Europe since March 2019, the black curve with normal traffic first and the maximum traffic in the summer months and stronger variations over Christmas and the end of the year. And then we have the strong reduction of air traffic since March 2020 until March 2021 here. And you see that was dramatic, partially exceeding 80%. The average over the months of April was about 80% reduction in air traffic over Europe in terms of the flight distance here. And we have similar analysis in terms of fuel consumption, etc., because we had all the Eurocontrol data to get a very reliable picture of flight activity over Europe and the North Atlantic also. So this was a situation. And you all know that aviation can cause contrails, and contrails can be observed in the sense that the outgoing long-wave radiation changes. You see here a picture of the brightness temperatures in the difference between 10.8 and 12 micrometer in the infrared. And this difference is sensitive to ice clouds, to thin cirrus clouds. So what you see in white is the presence of ice clouds. And you see that these ice clouds, they occur here over a region which you see better here on the right side, northern Germany, Scandinavia, England, you see here, and you see Italy down there, and so over Europe, Central Europe. And we do see partially line-shaped clouds, but also we see many amorph clouds on which we cannot easily say whether these are just cirrus clouds or whether these are merged contrail cirrus. And I can tell you these are mainly merged contrail cirrus clouds from the analysis which I show later. So this is the situation which we want to investigate. And the background for this has to do with contrail formation. Contrails form from the emitted water vapor, which the exhaust from the jet engines mixes with ambient air, and by this mixing, it of course dries because it mixes in dry air from the ambient air, but also cools. And because of the curvature of the saturation curve, which we will see in the next figure, we expect there could be liquid saturation somewhere reached, and then liquid droplets form, and the droplets on these droplets form particular on soot, which is co-emitted with the water vapor and other gases and the heat. And then these liquid droplets grow, and then they freeze because it's so cool, so cold. Temperatures below about minus 40 degrees centigrade. You have homogeneous freezing of ice particles, so you don't need an ice nucleus for that. It's just because it's so cool. You need the nucleus to get the droplet. And then the ice particles can grow and can form a visible contrail, which is very dramatically seen in this situation behind this 4-engine aircraft. So that's very well understood. In fact, there's a thermodynamic theory which explains much of it. We can consider the mixing of heat measured here in terms of temperature, and water vapor measured here in its partial pressure, which follows a straight mixing line from the engine exit to the ambient atmosphere. E is a point in the ambient atmosphere, certain temperature and humidity. The partial pressure is below saturation. The saturation pressure is the full curve here above, the liquid saturation. The dashed curve is the ice saturation. And the mixing line can vary has the same gradients, but comes to various points. And there's one threshold point. The LC point is a threshold for this situation with given humidity, where the tangent of the mixing line just matches this curved saturation curve. And in this case, you just get 100% relative humidity over liquid water at that place. And then, of course, you get some condensation. So anything which is cooler than LC causes a contrail. Any atmosphere that is cooler than that causes a contrail. So here you see a diagram which shows where contrails can form even for 0% ambient humidity. The lowest line is for the absolutely dry atmosphere. If it is cool enough, the pure water from the engine is enough to cause a contrail. Of course, if the ambient atmosphere is humid, if you have 100% humidity here to the right, then you get a contrail at higher ambient temperatures. And for orientation, the standard atmosphere temperature profile is drawn in here. So we expect contrails in the upper troposphere, lower stratosphere, maximum at around 11 kilometers in this case here. It depends on pressure. It depends on the emission index of water vapor and heat, and the propulsion efficiency of the aircraft engine. That's the only aircraft parameter which enters, but it's a secondary parameter. It's mainly the fuel. Okay, so that is the theory. Over the years, since about 2009, we developed a contra-zero simulation prediction model, short CoSIP. This model takes input in terms of aircraft information over the aircraft movements, the aircraft properties, like fuel consumption and span and mass of the aircraft, which we do need for computing the wake behind the aircraft, the wake vortex behind the aircraft. And of course, we do need methodology. And for this, we usually use ECMWF forecast data, which we think are the best for this purpose, with temperature, humidity, ice, water content, radiation, and also wind, etc., taken from those fields. And then we take the traffic and follow single sequences of waypoints, so coordinate flight tracks. And for each waypoint, we ask, is the ambient atmosphere cool enough so that a contrail can form according to the Schmidt-Eppelmann criterion? And is it humid enough? And then we start the black lines. The black lines are those traffic lines which are causing contrails. And then we investigate how the ice water content along such a flight track develops with time, how it is changed by wind shear, how the contrails are moved with the wind in a Lagrangian sense downwind, etc. And from this, we can then compute things like life cycle of the contrail, how long they live, the induced cover. We also can compute the radiative effects of that with some parameterized models. And we can also compute the cirrus properties and simulate that and compare it to observations. And then can make predictions for climate impact predictions of that. That has been done now in several studies. For example, we applied it for a case where we have observations with our research aircraft Falcon. You see its nose boom. The aircraft is flying into the wake of another aircraft flying ahead of us. And you see here the curtain with ice particles. These are the primary vortices where the contrails form originally. And then there's some humid air which rises above this sinking primary vortex in the secondary vortex. And we measured here all kinds of chemical components as they are listed here, NOx, HONO, SO2, and O. And we normalize the measured concentrations with the emission index. And then you see that all these trace gases follow a similar pattern because they are normalized to their respective emission indices. And we get maximum concentrations in the wakes, in the primary wake and lower concentrations in the secondary wake. So the depth here is the depth in the vertical normalized by the actual depth of this vortex. And here you see the ice particles that are measured, and they are also normalized to an assumed particle emission index for soot. And from you see that this normalization is not of the same quality as for the trace gases. So we get other processes play a role in addition to just mixing, namely particle formation in the wake and also some heating of the sinking adiabatically warming wake vortex. So all this has to be modeled, and the next plot shows a set of about 200 data points from in situ measurements in red, from remote sensing with LiDAR and from satellites in blue. And you see here the number of ice particles within the contrail as a function of plume age from 1 second to 10,000 seconds, so a few hours age. And that is a scatter of the measured data, of course, under various conditions, which one can discuss. And that is the scatter of simulations with a global model, which includes CoSIP as a submodel. And this CoSIP model here computes on average on the 50% median is here, the white line in the center part. And these are the maximum and minimum values which occur in a 10 years simulation. So these are climate model results. And you see these climate model results cover the measurements quite nicely here. That is for particle number of ice particles, that's ice water content, that's the particle effective radius, which is the 1 to 10 micrometer range, the visible optical depths, which can be measured with LiDAR, the contrail widths, and the contrail depths in the geometric widths and geometric depths can also be measured by all kinds of means, remote sensing in particular. And you see the computations, the white line in the center follows, which is the majority of results, follows the measured results pretty nicely. So that's a validated model in this sense. And this model has also a radiation transfer model, which parameterizes Libratrat results, so a complete radiation transfer model, which includes scattering and absorption and emission from cirrus and contrail ice particles of various shapes and various sizes. And so there's a scatter, the cloud of results because of various ambient conditions. And we see that the radiative forcing in the long wave is positive. It is maximum over warm surface, of course. It's not so large over cool surfaces. So it depends upon the surface temperature, or even more accurately on the brightness temperature of the Earth. And the short wave part during daytime is cooling even more than the warming part, up to 250 watts per square meter here. And it's, of course, maximum over the oceans because of the low albedo which we have there. So over a black surface, if you put a white cloud over a black surface, it can cool considerably. If you do the same over snow, the short wave effect is, of course, far less. So the effect is mainly a function of the optical depth, which is a parameter, time of the day, particle size, and particle shape. Okay, this is now an assessment that was published late last year, actually early this year, 2021, I should have said here. It gives here the radiative forcing for the year 2018 of the international global, of the total traffic for the year 2018 in terms of CO2 radiative forcing. So it's of the order of 30 or 40 milliwatts per square meter with a rather small error bar. The value is given here, 34 milliwatts per square meter. And for contrast, the mean value is 57, but of course the scatter, because of our limited knowledge here, and perhaps also because of the large natural variability of contrast zeros, even if you observe it, we will always have variability in our observations. So there's a large uncertainty, and I must say we probably will never get that uncertainty to a level comparable to that of CO2, because it's a far more complicated process which happens here to get contrail radiative forcing. But it's the largest of all. It's larger than from LOX and other things. I only show these two things here. Okay, now I come back to my case. When last year, since March 16, that was my birthday, last year in 2020, suddenly everything was shut down because of being afraid about COVID infections. So there were strong traffic reductions because of the politics which decided to do that. And so we got strong reductions in air traffic. This is here from flight radar, as you see, for the early times, but we have it later from Eurocontrol. And these are the numbers, number of aircraft, flight distance, fuel consumption, how they change. And that is the pattern of fuel consumption for 16 April 2019, so normal traffic, and for 16 April 2020, the reduced traffic. And you see it's a considerable reduction, as you know, of course, now. And then this is a picture which I showed again. And now the question is whether we can use this as a test case to test our modeling. That would be wonderful because we have all kinds of uncertainties in our model results, and that now drives the following research. At that time in April last year, we had not many data yet. So we just considered one day first. We couldn't consider this single day, but not only 1 hour, we considered all hours of that day. And this is the cloud coverage in terms of the optical depths of ice clouds over this domain, which you have seen as we derive it from Meteosat. So that is, of course, a tricky algorithm, which I can't explain here in this short time. How this is done by Luca Bugliaro and others in our institute. So we get a picture of where ice clouds are present. And in part of these ice clouds, you see embedded line-shaped clouds, but it looks more diffuse, I would say, on average. So this is the optical depths, and you see here the color scale goes typically to order 1. So the optical depth is of the order of 1, up to 2 maximum here on the left side. And that is now the simulation which we have. If we ignore any aviation traffic, if you take just the ECMWF data and the cirrus properties from that model and simulate the optical depths, assuming certain particle sizes, then we get a picture which has the same overall structure as observed, but doesn't have this line-shaped ingredients. Now, if we add the contrail pattern, then the changes are not so dramatic. You find some places, if one looks carefully, that there are additional line-shaped structures here, which you also observe in the satellite. So there is some, say, 60% or so correlation between what you see and changes and observations there. If you would take, this is for the traffic of 2020, if you do the same for traffic of 2019, then of course there will be far more contrails, and this picture cannot be compared to the observation. It shows that this is certainly not a good representation of what we observe. So there's certainly an observable impact of the reduced traffic on cirrus, and if all that would be from aviation, then you see that much of the cirrus is really because of aviation and not because of natural cirrus cloud is in that situation. Okay, now that has consequences for the radiative forcing. We can compute the local radiative forcing from the sum of all the contrails here, average over 1 day. Here is a function of latitude and longitude. Also, the mean values here for 2020, the full lines, and for 2019, the dashed lines. So you see a factor of 5 or so, of 6 reduction in these parts. The radiative forcing is positive where it is red, it is negative where it is blue. So we have a mixture of both. It depends upon the albedo. For example, over the North Sea, it's more cooling or more frequently cooling. It depends on the temperature and on the altitude and on the presence of other clouds above and below these cirrus clouds. All that is included in this model. Okay, then we started to extend that for 6 months and then for later for 12 months. And of course, we were aware that if you compare 2020 with 2019, you cannot assume that the cirrus situation in both years was the same because of same weather. In fact, it was not. If you look to the global solar surface irradiance, the amount of heat coming from the sun down to ground, then this is a situation for 2019. We had more solar sunshine over the Mediterranean countries, as you would expect, and less over England. And we the difference 2019 2020 is dramatic. It goes from minus 20 watts per square meter to plus 20 watts per square meter. So these are the differences based on ECMWF data between the 2 years, actually the 6 months period in the 2 years. And so we cannot simply expect that by comparing the 2 years, we get the effects of aviation. It's overwhelmed by natural variability. This is a potential contrail coverage. That is the area where the temperature is below the Schmidt-Eppelmann criterion, which I explained to you, the thermodynamic criterion, and the relative humidity over ice was above 100%. Then you expect that any aircraft that flies here forms a contrail, so the maximum here west of Ireland, incidentally, in that period. And this is the difference between 2019 and 2020. There is about 6% difference in potential contrail coverage over the 2 years just because of different weather. So the weather certainly plays a significant role. So what we then do is we take observations, not zeros cover, but also of the reflected shortwave radiation and of the outgoing long-wave radiation. These two terms can be computed from weather models, but it also can be observed with meteosat, at least approximately. And of course, we have the solar direct radiation that can easily be computed because you know longitude, latitude, and time. So that's well known. The incoming solar direct radiation, the reflected, can be measured and computed, and the outgoing can be measured and computed. Now, if you add a cirrus cloud to that, then of course you get more reflected solar radiation. So the reflected solar radiation increases if there is a cirrus cloud, and that implies that there's a cooling because of more reflection of energy out to space. So there's a negative shortwave radiation forcing from an additional cirrus cloud. The opposite is true for the long-wave part. The outgoing long-wave radiation gets reduced if there's a cirrus, and that reduction causes a positive warming for the Earth system because more heat stays below that cirrus cloud in the atmosphere. So we have short-wave and long-wave effects, which are abbreviated with SW and LW here on these slides. And you have to remember RSR and OLR, they come now in the plots again. Now, these are is a complicated set of plots, I agree. This shows 6 panels. Let us first look to the lower parts, the 3 lower panels. This is the pure CoSIP result on average over 6 months, and it shows a change in optical thickness between the years 2019 and 2020, 6 months of it, starting in March 2019 or 20. And so we expect that there should be, in 2019, more contrail cirrus in terms of optical depths in that area. We also expect that there should be less outgoing long-wave radiation, therefore blue, which is cooling, and we should have more reflected short-wave radiation because of the presence of cirrus. That's what the model says. This is what the data say. This is based on meteosat data, say for outgoing long-wave radiation and reflected short-wave radiation, after subtracting what the ECMWF model computes for all RSR. Here I assume that the ECMWF does not model contrail effects. Certainly the ECMWF does not have a model to compute contrail effects, and the data assimilation process is at best very weakly sensitive to contrail cirrus properties. There are various arguments for that, which I cannot repeat in short here, but it's the fact that ECMWF does not include contrails in a significant amount. So what we now see, that there's a blue area here and a blue area there. There's a red area here and a very dark red area over there. Here, red areas, and there are red areas. So you see some correlation between the models and the observations, but certainly a weak correlation. And any significance here can be asked about. It's just 6 months of data. It's too little to make reliable statistic on that, but it is promising. It shows you that there is some signature in the data, which you find also in the model and vice versa. Now we repeated that for 12 months, and you see the signature stay. So this 12 months results show very similar comparisons, so with slightly different patterns, because of course the traffic changed differently between the second half of 2009 and the second half of 2020. So that is included here, and this supports that these partial similarities that we see, not overwhelming, are partially caused by aviation. So in fact, that's already what I can tell you, namely that air traffic reduction during the COVID-19 pandemic provided a test case for aviation-related forcing. There are, with some goodwill, aviation contrast signatures identifiable in spite of strongly different atmosphere and surface conditions in 2019 and 2020. Remember, we had 20 watts per square meter change in solar radiation at the surface, but perhaps 1 watt per square meter change because of contrails. So it must be a small contribution to the overall. Therefore, of course, we do need further model studies. First, to cover longer time periods, and work is in progress. To do that, we can cover the last 10 years, and etc., and which had changing traffic patterns. We include other emissions like the NOx from aviation and aerosols from aviation and also from other sources. So we need a more complete model, which includes all that. And that will keep us busy, I guess, for the next years to get a more comprehensive understanding of the observed changes. So we do not have a final result. We have intermediate results. Contrails do contribute a large share to aviation's climate impact. That's likely true. It's not finally proven, but it is very likely true. And if you would avoid contrails, that would be the effective mitigation potential, because avoiding contrails today would have a reduced radial forcing for tomorrow. So that would be very effective and would help immediately to reduce the warming of the globe. Thank you.
Thank you very much, Ulrich. Very interesting talk. So if there are any questions, please put them in the chat, but perhaps I'll kick things off. So I was interested to hear a bit about the contrail model. And you noted that there was various inputs that the model takes, including meteorological inputs from the ECMWF. Yes. And I think you had a slide that showed that the model reproduced some of the observed contrail properties from in situ data quite well. Do you find that the contrail, the simulated contrail properties are quite sensitive to the choice of meteorological inputs?
We have various sets of comparisons which indicate errors of the order of 30 to 50%. There's a recent paper which says a factor of 2 to 3 error, which I don't believe. I think that is an over-stressing of the point. I can't believe that. In fact, my model shows that usually the ECMWF data lead to an underestimate of contrail zeros, not an overestimate of contrail zeros. So we have to artificially enhance relative humidity a little bit by a 5 to 10% to get a good best agreement with observations. Yeah, it's very important to have high resolution in the computing process.
In terms of the resolution of the input data as well,
clouds and the zeros, etc., are
what you
simulated.
Want pretty high.
The output then, if it comes as half a degree or a quarter of a degree, to me, to then run the COSIM model in it is not so important, because I simulate the contrail on the meter scale with a Lagrangian model. So my contrail width is 10 meters, yeah, regardless of what the ECMWF resolution is. Thank you.
Okay, great. So thanks, Ulrich. If there's any more questions, then please pop them in the chat. Thank you very much. So I'd like to welcome to the stage now Melanie Hammer from Washington University in St. Louis.
All right.
Hi, Melanie. Over to you. Over to you.
So the strict lockdowns globally in the early part of the COVID-19 pandemic have provided an unprecedented opportunity to examine the impacts of human activity on air quality. So very early in the pandemic, satellite images were released showing dramatic decreases in tropospheric NO2. For example, over China, decreases of as much as 50% were observed. So anthropogenic NO2 is mainly produced through combustion processes, with transportation and industrial processes being major contributors. And these sectors were obviously greatly impacted by the lockdowns. So these dramatic decreases in NO2 then prompted the question of what the potential impacts of the lockdowns were on PM2.5 concentrations, as NO2 is actually a precursor for PM2.5 formation, and NO2 and PM2.5 are both emitted from several of the same sources. So the effects of the lockdowns on PM2.5 are of particular interest from a human health perspective, as PM2.5 is the leading environmental risk factor for mortality globally. And there's also increasing evidence that exposure to air pollution actually leads to increased negative COVID-19 related outcomes. So PM2.5 is emitted from a variety of sources. Anthropogenic ones, such as industry and power plants, residential combustion, transportation, and agriculture. And it's also emitted from natural sources, such as blowing dust and the emissions of biogenic VOCs. So these emissions can be either primary or secondary sources of PM2.5. And the PM2.5 components that are considered primary are those that are emitted directly from their sources as particles. So these would include black carbon, primary organic aerosols, dust, and sea salt. And we can consider these kinds of particles to be pretty linear in terms of their relationship with their emissions. So then there's also secondary PM2.5 particles, which are formed in the atmosphere through the gas to particle conversion process. And secondary particles, secondary components of PM2.5, include secondary inorganic and organic aerosols. So secondary inorganic aerosols include the sulfate, nitrate, ammonium system, which is formed through the gas to particle conversion of sulfur dioxide, nitrogen oxides, and ammonia gases. So this system in particular can be highly nonlinear in terms of the relationship between emissions and aerosol formation. Therefore, a substantial reduction in NOx emissions may not necessarily result in a substantial reduction in total PM2.5 mass. And in fact, initial studies examining the effects of the lockdowns on PM2.5, which used mainly ground monitor data, found results in line with such a nonlinear chemical response. So several studies showed that even with the strict restrictions put in place in China, there were several severe haze episodes, particularly over northern China. And these episodes were found to be caused by a combination of stagnant meteorological conditions and increased secondary aerosol formation from power plant emissions. And this was despite substantial reductions in transportation and manufacturing emissions. And then initial studies examining air pollution over the US and Europe found that although there were mostly substantial decreases in NOx, there were little to no decreases in PM2.5. And so these initial insights into the PM2.5 system based on sparse monitoring motivate a more comprehensive assessment that includes satellite aerosol observations. So for the past decade, our group has been developing spatially complete satellite-derived PM2.5 estimates. And our method starts with combining aerosol optical depth, or AOD, from several satellite products. And the AOD is a measure of the total extinction over the atmospheric column due to the presence of aerosols. And satellite AOD retrievals therefore provide a global picture of the total column aerosol abundance. So we combine the separate AOD products based on the relative uncertainties with AOD measurements from the Global Sun Photometer Network AeroNet, which measures AOD with a very high degree of accuracy. And because AOD represents the aerosol abundance of the total column, we then need to extract the aerosol information at ground level. And we do this by using the Geoschem chemical transport model to simulate the coincident ratio of simulated surface PM2.5 to total column AOD. And this ratio is a function of the factors that relate PM2.5 mass to satellite observations, such as aerosol size, aerosol composition, diurnal variation, relative humidity. and the vertical structure of aerosol extinction. So the resulting global satellite-derived estimates, which are purely geophysically based, so that means they're comprised solely of satellite data and information from the chemical transport model, show excellent agreement with ground monitor data. And this is important because these geophysical estimates are completely independent of the ground monitor data. So this gives us some promise that we're actually capturing PM 2.5 even in regions with sparse monitoring, which is unfortunately still most of the world. However, there are some regions such as North America, Europe, and China, which have quite dense monitoring networks. And so to take advantage of the valuable information provided by ground monitors where they exist, we use geographically weighted regression to predict the bias between our geophysical estimates and ground monitors. And then we use this bias as an adjustment to produce our hybrid statistical geophysical estimates. And so these hybrid estimates explain only an additional 11% of the variance in our estimates when comparing with cross-validated ground monitors. So this means that the majority of the information provided by our estimates is actually through our geophysically based approach. So for this work, to examine the effects of the COVID lockdowns on PM 2.5 concentrations, we produced monthly regional estimates over China, Europe, and North America. So these are regions with considerable monitor density, and they're also regions which experience prolonged strict lockdowns. So we produced the monthly estimates for January to April 2018 to 2020 in order to compare PM 2.5 during lockdown months to the same time period in previous years. And then based on multiple sources suggesting which months had the largest emission reductions, we consider February to be a lockdown month for China and April to be a lockdown month for Europe and North America. So first, we are looking at the PM 2.5 concentrations in China during the lockdown period compared to the same time period in the previous 2 years. So the three left panels here show the February mean satellite-derived PM 2.5 concentrations for 2018, 2019, and 2020. And then ground measurements are overlaid in filled circles. So overall, we see similar spatial patterns between years, except for regions of Northwest and North Central China showing increases in PM 2.5 in 2020. And the North China Plain region, which shows a substantial decrease in 2020. So the increases in Northwest and North Central China are in close proximity to the Gobi and Taklamakan deserts. So those are actually likely more influenced by natural variability in desert dust rather than the lockdowns. However, over the North China Plain, the main sources of PM 2.5 are anthropogenic. So in the right column of this figure, I'm showing the differences in February mean concentrations between 2019 and 2018, between 2020 and 2018, and then 2020 and 2019. So the North China Plain region is outlined with a black box, and we see that between 2018 and 2019, concentrations actually increased over this region, while the 2020 and 2018 and 2020 and 2019 differences have switched to substantial decreases. And then if we look at the differences in January mean PM 2.5, which we take to be the non-lockdown period, we see increases in PM 2.5 in 2020 compared to the previous 2 years. So this is similarly shown in the bar chart to the right there, which shows the population weighted mean PM 2.5 concentrations over the North China Plain. So we see that concentrations increased in January 2020 compared to the previous 2 years, while concentrations substantially decreased in February 2020 compared to the previous 2 years. So this suggests that this feature could be related to reduced anthropogenic emissions due to the lockdown. And so here are the results over Europe during the lockdown period. All 3 years show very similar spatial patterns, with lower PM2.5 concentrations in Western than Eastern Europe. And there really aren't any obvious dramatic differences in 2020 compared to the 2 previous years. And if we look at the difference plots to the right, we see that the interannual differences are strongly dependent on reference year. And really the only feature that stands out as potentially being a decrease due to the lockdowns is a decrease over the Benelux region in 2020 compared to the previous 2 years. And so then if we look at the January to February differences, which we're taking to be the non-lockdown period, we see similar interannual variability to that during the lockdown period, except for that decrease over the Benelux region. So overall, these differences suggest that the lockdowns had pretty minimal effects on PM2.5 over Europe. And so then here are the PM2.5 estimates over North America during the lockdown. Looking at the left panels, once again, we see very similar spatial patterns between years with no obvious features in 2020. And if we look at the difference plots to the right, we again see that interannual variability is strongly dependent on reference year. And in fact, we see some of the smallest changes in 2020 versus 2019, with the differences being well within the calculated uncertainties with data. And so then if we look at the differences between years during the non-lockdown period, we see overall pretty similar spatial patterns in the differences as during the lockdowns. And so one feature that somewhat stands out is a region of decreases near the Great Lakes, which is not seen during the non-lockdown period. So this feature could potentially be related to the lockdown. So in order to provide some insight into the reasons for the extent of changes in PM2.5 during the lockdown periods, we conducted sensitivity simulations using GeoSchem to investigate how emissions and meteorology may have influenced PM2.5. So in the left column, I'm showing the results of a sensitivity simulation where NOx emissions were reduced by 50%. While the right column shows the results of a sensitivity simulation where all transportation-related emissions were reduced by 50%. So we see in both cases, the decreases in PM2.5 occur primarily near major urban and industrial regions. And some of the simulated decreases align somewhat with the observed changes over the North China Plain and Central Europe. However, emission reductions alone don't seem to be able to explain most of the observed changes. And so here we're looking at the changes in PM2.5, but on a components basis for secondary and organic aerosols. And this is showing the scenario where transportation emissions were reduced by 50%. So these changes really are demonstrating some of these non-linearities associated with this aerosol system. So along with the expected decreases in nitrate aerosol, we see that emission reductions actually resulted in some small increases in sulfate, as well as changes in ammonium across all parts of all 3 regions. So these increases in sulfate partially offset some of the aerosol decreases, which could be a partial explanation for the muted effect of lockdown emission reductions. And so then here are the changes associated with the 50% reduction in NOx emissions scenario. And we actually see some of those non-linearities are even more exaggerated with some larger increases in sulfate. And So we then examined the effects of meteorology on PM 2.5 changes during the lockdown periods. So for this sensitivity simulation, emissions were held constant between 2020 and 2019, and only meteorology varied. So any changes in PM 2.5 would be solely due to meteorology. And this simulation was able to explain the majority of changes in PM 2.5 observed during the lockdown periods. So over China, we see those increases over the northwest and north central regions. However, we don't really see the region of decreases over the North China plain. And then over Europe, we see meteorology can be attributed to a majority of the decreases. And then over North America, most of the observed changes are reproduced, and we do see some of the decrease over the Great Lakes region is reproduced. So we then conducted a sensitivity simulation where the changes in PM 2.5 are due to meteorology, plus a 50% reduction in transportation emissions. So overall, the spatial distribution of changes is similar to when just considering meteorology. However, we now can see the region of decreases over the North China Plain start to appear. So this suggests that this feature is mostly due to a reduction in emissions and is likely a result of the lockdown measures. And then we also see a slight further enhancement of the decreases over the Great Lakes. So this suggests that this feature might be caused by a combination of natural variability as well as emission reductions. And these results actually echo the conclusions from a recent study from our group looking at the sectorial contribution of sources to global PM 2.5. And that study found that transportation is actually a modest contributor overall to PM 2.5, and residential and energy sources are dominant contributors. And those sectors were much less affected during the lockdowns, so that could be a partial explanation for the changes we're seeing. So the role of PM 2.5 as the leading global environmental risk factor for mortality, coupled with emerging evidence of the association of ambient PM 2.5 and negative COVID outcomes, motivates attention to assessing ambient PM 2.5 concentrations during the pandemic. However, sparse ground monitor data, as well as a latency in the availability of such data, motivates alternative measures of obtaining PM 2.5 from satellite remote sensing. So in this work, we produced monthly satellite-derived estimates of PM 2.5 to examine the effects of the lockdowns. And we produced our estimates for January to February 2018 to 2020 over China, Europe, and North America, regions that had extensive ground monitor coverage and that also put into place strict prolonged lockdowns. So despite the widely reported dramatic reductions in ambient NO2 concentrations during COVID-19 lockdowns, we find that evidence of PM 2.5 reductions specifically associated with the lockdowns is harder to discern. So we find evidence that concentrations did decrease over the North China Plain region during the lockdown due to a combination of emission reductions and meteorology. However, over Europe and North America, we did not really find evidence of any significant changes, except for perhaps a small feature over the Benelux region and over the Great Lakes region. So this work demonstrates the complex relationship between PM 2.5 and its emission sources, and the importance of natural variability on short-term changes in PM 2.5. And the data set used in this work is available from the below Zenodo link. However, recently Aaron Van Donkelaar and our group published new global monthly PM 2.5 estimates for 1998 to 2019, and we will be releasing 2020 in the near future. And so these estimates were calculated with an improved algorithm that allows for obtaining monthly global concentrations along with their associated uncertainty values, which is a really exciting new development. And these estimates show really excellent agreement with ground monitors. And so you can download the entire data set from our website using the link there. And thank you for listening.
Nice talk, very clear. So questions, I'll just look in the chat. Zongbo as a comment, interesting simulation results.
Okay.
Their group showed similar increase in sulfur and nitrogen conversion rates during lockdown. Seems to be consistent with what you've shown. The question is, how do you disentangle the impact of meteorology? And
I'll just answer the 50% decrease in transport first.
Why did you decide to use 50% decrease in transport emissions?
At the time, the literature was suggesting like pretty varied results about exactly how much traffic emissions were reduced, and it kind of varied between 25 and 75%. So we picked 50%, but we actually did do sensitivity simulations using 75%, and there wasn't much of a difference from the 50% case, so we just kind of stuck with that. But so to answer the question about meteorology, like I actually did include this extra slide. So basically, meteorological conditions affect PM 2.5 in several ways by altering normal emissions, influencing photochemical production, advection, or depositional loss. And so through our sensitivity simulations, we could look at the effects of meteorology on PM 2.5 in a components basis. And so the most prominent changes were seen in desert dust. So essentially, factors such as higher wind speeds could increase dust emissions. And so that's consistent of those features we're seeing near the desert regions in northern China. And then we also see decreases in dust in southeastern Europe. So this suggests like maybe a change in the advection pathways of dust from source regions from like the Sahara or the Middle East. And then we also see a decrease near the Sonoran Desert region in southwestern North America. And then we do see influences on the organics and secondary inorganics, but they're weaker and a little more complicated. So there's an increase in organic and secondary inorganics over northeastern China. And this is likely driven by factors such as shallow mix layers or stagnant conditions or even reduced precipitation. And then over southeastern China, organics and secondary inorganics decreased, were likely influenced by increased precipitation or warmer temperatures, which decreased nitrate. And then over central northern Europe and kind of like the Great Lakes region, there's probably multiple processes affecting those changes, like affecting the accumulation at the surface, the aerosol formation processes, and as well as like depositional loss.
Okay, thanks. Just a final one, perhaps for me. You did talk through the method, how you produce your PM field. It's the AOD with some information from the CTM on the relationship to the surface field. So does this include like the ground monitor data as well? Is that just purely used for
ground monitor
validating
data at all? This is just the GeoSChem simulation. but then like, okay, here, like the concentration maps in the background, like those would be the hybrid estimates, including the ground monitor adjustment. Yeah. Thank you.
I see. Okay. Brilliant. Well, thanks for that talk. Thank you. Okay, so our final speaker this afternoon is Susan Annenberg. And so if you'd like to come to the stage, please, Susan. Susan's from George Washington University.
Great, excellent. Thank you so much for inviting me here. It's really a pleasure for me to be here with you today. And I had the pleasure of watching most of Melanie's presentation.
Really interesting talk.
For that, Melanie. Unfortunately, I missed most of the other ones. So hopefully I'm not repeating some of the information that was already given, but I'm really looking forward to the discussion here today. So what I'll be talking about today is some work that my group has been doing over the past year and a half, looking at inconsistent nitrogen dioxide drops during COVID-19 lockdowns with a specific focus on US cities. But I'll also speak about some European cities towards the end of the presentation. And the idea is that we can learn from these NO2 drops during this natural experiment to learn ways that we can protect near-term public health, considering that air pollution is a contributor to COVID-19 severity and fatality. And also we can learn some things about how to design longer-term environmental policies to protect public health. So I want to thank my many contributors. Much of this work that I'm presenting today was led by Dr. Dan Goldberg and Dr. Gage Kerr from George Washington University, with some very valuable contributions from some of the other folks listed here. And we had support for this work from NASA. So I just want to start with why we study nitrogen dioxide. And many of you have already know this, of course, and I'm sure it was discussed earlier today, but just to give maybe a little bit of a different spin on it, that of course nitrogen dioxide is a tracer for urban traffic. It's a combustion-related air pollutant in cities that primarily comes from traffic, and so it can be quite valuable to study for environmental policy planning. How can we ensure that our cities have safe air to breathe in the future? And what are the contributing factors, the contributing sources to traffic-related air pollution in our cities? Secondly, NOx emissions, of course, are precursors to PM 2.5 and ozone, which are the dominant contributors to the burden of disease from air pollution. So it's very important for us to understand how to control NOx emissions to reduce that burden of disease from both PM 2.5 and from ozone. But also NO2 itself is associated with health outcomes, and epidemiological studies are relatively consistent that NO2 exposure is associated with pediatric asthma development. That's not just asthma exacerbation, but asthma development, new cases of asthma. And the evidence is much more consistent for nitrogen dioxide compared with PM 2.5 and ozone in terms of the role in pediatric asthma development. Although, of course, we don't know for sure that it is NO2 itself. It could be a marker for something else in the traffic-related mixture. But nevertheless, NO2 is a very good proxy for traffic-related air pollution in cities. And then finally, a more convenient element here is that space-based NO2 columns are very highly correlated with ground-level concentrations, which makes it, again, a very convenient pollutant to be studying compared with something like PM 2.5, which has more disparate sources, regional in addition to local, and the link between aerosol optical depth, what the satellite sees, and ground PM 2.5 concentrations is not necessarily as tightly correlated. So it's very convenient in terms of trying to understand how air pollution varies within the city, and the fact that we have space-based instruments that are continually monitoring NO2. And so when we're faced with an unexpected natural experiment like COVID-19 lockdowns, we already had this monitoring infrastructure, the space-based monitoring infrastructure out there taking images of our air quality, and we can use those data to track how air pollution changed. I just wanted to dig a little deeper into why NO2 is important from a health standpoint, because this is relatively new literature. But our group has been developing methods to estimate the burden of disease from NO2 pollution on pediatric asthma incidence. So like I said, the epidemiological evidence is relatively consistent that there is this association between NO2, potentially itself, but also potentially as a marker for the broader traffic-related air pollution mixture, and pediatric asthma incidence. And we wanted to know, well, how much does that really matter in our cities? And so we estimated the fraction of new pediatric asthma cases each year that could be attributed to NO2 pollution. And these are the results. We found that that fraction actually ranges from as low as 6% all the way up to 48%, and that was in Shanghai. So what that indicates is almost half of new pediatric asthma cases in Shanghai could be attributed to NO2 pollution. And what's interesting to note here is that this is not a phenomenon that is limited to just developing cities. This is relatively consistent. The large contribution of NO2 to pediatric asthma incidence is relatively consistent across cities in developing cities as well as in high-income cities. So just take a look at Washington, D.C. in the high-income region where I live. We're at about 25%. That means that about a quarter of our new pediatric asthma cases in Washington could be attributed to NO2 pollution. So when the lockdown started, it was in March for us in the US, Dr. Dan Goldberg from George Washington University was already using the TROPOMI satellite sensor to explore how NO2 differed across cities across the United States and how those were trending over time. And so in fact, he was sort of perfectly placed to try to get at this question of what did everybody, starting to stay at home, what did that do to NO2 concentrations across the United States? And so, this was a map that he had already been working on prior to the lockdowns for mid-May 2018 to the end of December 2019, basically the entire TROPOMI record at the time. And you can see that the NO2 concentrations are highest in the urban areas. Again, not surprising, it's very urban pollutant. But, TROPOMI was flying, and we were able to track how those changes occurred. And so Dan was kind of relatively quickly able to turn around a map like this, showing how NO2 changed over the entire United States. And anywhere you see blue here is where NO2 was lower in 2020 compared with 2019. And, at the time, there were a lot of news articles coming out showing, for Washington, D.C., again, where we live, how much cleaner the air was. For Los Angeles, we could actually see the skyline of the city, which was not possible before. And so there was a lot of hype about how the air was getting cleaner. And at the same time, we were having a lot of wet and windy weather across the eastern half of the country, as well as in Los Angeles. And so, we were wondering how much of this NO2 drop that the media was reporting on was actually driven by the anthropogenic emission changes versus the seasonal effect that was happening and the wet and windy weather that was happening simultaneously. And so we wanted to know what would this map look like if we kind of took meteorology out of the equation here, if meteorology was normalized out and we just created a map of the impact of the anthropogenic emission changes. And then we also realized at the time, this is an unprecedented situation we are living through, where we have unprecedented NOx emission reductions, or at least an unprecedented human activity change. And at the same time, we have the most highly resolved, geographically complete, and highest the full temporal coverage that would be needed to observe how NO2 concentrations changed using that satellite record. So we could actually use that satellite record to understand what this reveals, what this natural experiment reveals about environmental justice issues related to air quality. There's been a lot of research in past decades showing how, despite the success of the Clean Air Act in the United States, air pollution remains inequitably distributed, with communities of color and with lower educational attainment and income levels experiencing higher levels of pollution. So could we use this natural experiment to explore how different subpopulations fared in terms of the improvement in their air quality? And then finally, we wondered, what are differences in the makeup of transportation and the degree of social distancing, how did that contribute to the levels of changes in NO2 that we were experiencing? So just to get at that first question first is, trying to normalize, to take the meteorology out of the equation, disentangle meteorology from the anthropogenic emission changes. Dan had already been creating these graphs showing how seasonality, wind speed, and wind direction have major influence on NO2 concentrations across these major US cities. So just take the seasonal change, for example. If you look at the change in NO2 concentrations observed by TROPOMI from March to June, which is exactly when the lockdowns were happening in the United States, we see this natural drop in NO2 concentrations, and this is prior to the lockdowns in 2019. So just naturally, the seasonal change was keeping NO2 concentrations low during this time frame. Wind speed also matters. So the higher the wind speed you have, the lower the NO2 concentration. We were having very windy weather around this time. Wind direction, of course, also matters based on upwind sources. And so, of course, these natural effects should have a very large impact on the NO2 drops that we were experiencing. So Dan used several approaches to try to disentangle natural variability from COVID-related lockdown changes. And I'm not going to go through this in detail. Please check out the paper at the bottom left-hand corner here. But just to say that we used one method that did not account for meteorology. Method one here accounted for the seasonality, but not the daily meteorology. And then methods 2 and 3 were two different approaches for accounting for both season and meteorology. And let's just take a look at the 20-city average across these US cities on the right-hand side here in the red box. We see about a 40% drop in NO2 if you do not account for any natural variability. So that was basically what was observed across these cities, is about a 40% drop in the TROPOMI NO2 amounts. But once we removed meteorology from the equation, it was more like a 20% drop. So about half of those NO2 drops during COVID-19 lockdowns in these US cities were due to meteorology and natural influences, and the other half was due to anthropogenic emission changes. Now, as I mentioned, one of the benefits and convenient factors of using satellite NO2 is that it's highly correlated with ground observations. And so you can start to tease out, the actual human experience on the ground from these satellite estimates. So this is just showing that correlation here for air quality monitors that are not near roadways or that are near roadways. And you see that TROPOMI is much more tightly correlated to those ground observations that are not near roadways, and it's likely under predicting estimates that at monitors that are near roadways. But nevertheless, we felt this correlation was so good that we could start to look at these human factors like environmental justice issues and health effects. So Dr. Gage Kerr, who's a research scientist working with me at George Washington University, conducted this environmental justice analysis looking at the demographic subgroups and the level of nitrogen dioxide drops that they experienced. So we've categorized this here according to the census tracts across the United States that had the largest drops in NO2, that had average drops in NO2, or the smallest drops in NO2. And we actually found something that was counter to what we expected. We had expected, or at least I'll just speak for myself, I had expected to see that the largest NO2 drops occurred in communities that were more white. The opposite happened, though. If you look at panel G here, the census tracts that had the largest drops in NO2 were actually the more diverse census tracts. They had more diversity than the census tracts that had the smallest drops in NO2. Same for ethnic background. In panel D, we saw that the census tracts that had the largest drops in NO2 were more ethnically diverse than the census tracts that had the smallest drops in NO2. And so, maybe a good news story that the communities that are more marginalized across the United States actually experienced larger drops in NO2. And yet it is not that clear. And in fact, it's much more concerning with that. So Gage took this a step further and lined up for a baseline period, the baseline period prior to the lockdown, shown in the solid connector bars here, how NO2 concentrations in the least white census tracts, shown in the orange dots, compared to the NO2 concentrations in the most white census tracts across these US cities. So let's just take a look at the all category at the top here. This is all census tracts across the United States. we see that NO2 concentrations in the baseline period, again with that solid connector line, were about double in the least white census tracts compared with the most white census tracts. Now, during the lockdown period, as shown with the dashed connector line, both the orange dots and the blue dots shifted left, and that indicates a lowering of NO2 concentrations during the lockdown from the baseline. And so again, that's great that NO2 dropped in both the least white census tract and the most white census tract. But take a look at the orange dots connected to the dashed line compared with the blue dots connected to the solid line. This shows that NO2 concentrations in the least white census tracts during the lockdown were still substantially higher than the NO2 concentrations in the most white communities prior to the lockdowns. So what this tells us is that these disparities in the baseline were so large that even the approximately 50% drop in passenger vehicle traffic that we experienced did not eliminate those disparities. In fact, those disparities persisted even during COVID-19 lockdowns. And you can see that pattern across all of these US cities. Some of them have more disparities than others, but they're relatively consistent. And this pattern also holds for income and for educational attainment. Now, as I mentioned at the beginning, we were also interested in trying to understand the drivers of these inconsistent effects across cities. So now that we've normalized by meteorology, we've explored how different subpopulations fared. We want to know, well, what are the contributing factors to these inconsistent drops in NO2 across these cities? We partnered with C40 cities, and we expanded actually mostly to European cities. And the reason is that we really wanted to get on the ground data on traffic, on the fuel mix of the passenger vehicle market, and on monitored air quality levels. And we were able to obtain that from all of these European cities. We have a smattering of additional cities included here. So you can see, for example, Santiago, Mexico City, Auckland, Los Angeles. But mostly these are European cities with real data that we were able to obtain through C40 cities. And what we found here is that the larger the percent of the market share of diesel the larger contribution of diesel in the passenger vehicle market, the larger the drop in NO2 during COVID-19 lockdown. Perhaps this is not surprising to folks who have been studying the emissions coming from diesel vehicles and how those have been higher than predicted from lab-based measurements. But nevertheless, I think this is confirming to see that cities that have higher proportions of diesel in their passenger vehicle market saw larger drops in NO2 pollution during the pandemic. And this kind of analysis can give us an estimate for, if these cities were to transition to lower percentages of diesel in their passenger vehicle market, as is somewhat happening, what could be the drop in NO2 concentrations that they might experience. We're digging into this further in the United States. The fact that we did not see that those NO2 disparities were eliminated during the pandemic tells us that there's some other contributing factor to NO2 disparities that wasn't really affected by the pandemic. So, obviously the light duty passenger vehicle sector was the most impacted and is a contributor to these NO2 disparities. But we took a look at the locations of power plants and industrial plants and roadways, highways to communities of color across the United States. And we started narrowing in on heavy duty trucking being the most geographically co-located with communities of color. And so we started digging a little bit deeper in the United States. This is now work in progress, to try to understand, can we use satellite data to pick up the signal from just the trucking related pollution? As our cars are getting quite a bit cleaner, as you may know, in the United States, we only have about 3% diesel in our passenger vehicle market share. So it's not the same situation as in Europe. We actually have somewhat clean light duty vehicles at this point. So we want to take a look at the heavy duty vehicles, and we know those heavy duty vehicles are quite a bit more polluting. And we have new sources of those trucking activities that are popping up. So we have the changing e-commerce that is leading to warehousing with a lot of trucking around it. We have oil and gas facilities that are popping up with quite a bit of trucking activity. And can we use the satellite data to tease out that contribution of trucking to NO2 pollution levels? And here's just two snapshots where you can start to see how this can come into play. On the left-hand side, these are two images of tropomi NO2 over the DC area, Washington, DC area. And we see on the left-hand side, this Sterling area where there's a lot of warehousing activity has much higher NO2 concentrations compared with even Dulles International Airport. Now, this was 2020, so our airport had a lot less activity compared with normal times. But still, the fact that we can see this warehouse activity area popping out indicates that we could potentially pick up this signal from trucking on NO2 pollution. Take a look at the right-hand side here where you have DC in the bottom left-hand corner and Baltimore in the top right-hand corner. We have two main roadways that connect these cities. One is I-95, which allows trucks, and the other is the Baltimore-Washington Parkway, which prohibits trucks. And you can see that there's a lot more red around Interstate 95, potentially indicating that trucking is leading to higher NO2 concentrations on that roadway compared with the roadway that prohibits trucks. So we're digging into this further to try to understand the role of heavy-duty trucking on NO2 disparities across the United States. But just to conclude, satellite-derived NO2 concentrations we found to be particularly valuable for understanding the inequitable distribution of air pollutants and their health impacts. And there's a few reasons for that. One is that compared with total PM mass, NO2 has a shorter atmospheric lifetime. It has less influence from regional pollution sources, as sharper gradients near emission sources, and that satellite NO2 column observations are very tightly correlated with NO2 observed at the ground. And so we actually have an observational record of the spatial patterns in urban combustion-related air pollution, which we are only able to really guess at using modeling approaches for other pollutants like PM 2.5. We expect this to get even better as new satellite instruments, new geostationary satellite instruments like TEMPO, which will be launched next year of the United States, will further increase the environmental justice relevant satellite record for nitrogen dioxide. And we wrote a brief paper on this, leveraging satellite data to address air pollution inequities, if anyone is interested in checking that out. We also have a NASA funded team called the Satellite Data for Environmental Justice Tiger Team. And we are linking satellite data with EJ mapping tools, environmental justice mapping tools, and with community groups that are worried about things like trucking traffic around their communities to try to understand how we can leverage that high spatial resolution and long temporal record of satellite-based NO2 estimates to shed light on overburdened communities and how we might reduce the burden that those communities are experiencing. So thank you very much. I look forward to the discussion.
Okay. We've got a few questions in the chat. I'll just kick off with one. Is there any evidence that other sectors other than road transport,
if you look at that spread among
these regions,
the NO2 drops that were experienced in urban areas, I showed a couple of figures of this for the United States, for 20 cities across the United States, and then about 20 cities across Europe. Some of that spread had to do with the level of traffic and the level of trucking in those cities, but there's quite a variety of sources that are influencing these cities in different ways. So we've got airports, we've got some of the coastal cities have shipping ports, we've got industrial plants and electricity generating units, whether or not those are coal-fired or some other generation approach. And so there is a bit of heterogeneity in terms of the other sources that might be contributing to those drops. But the passenger vehicle sector was really the most affected by the pandemic. You can argue that maybe plus or minus 10%, some of these other sectors were affected by things like people having their groceries delivered or increasing their deliveries of other goods. But I think for the most part, it was the passenger vehicle sector. We dug into this a little bit more in Gage's paper and have a couple of graphs showing how these other sectors were not really that affected by the pandemic. But I think locally, you know, anytime you're doing this kind of study across many cities, you might be missing some intricacies at the single city level. So for any individual city, there could be, you know, more complex things happening.
Okay, thank you. So just looking in the chat then.
Yeah, great question. I mean,
a question. He asks, how did you
evaluate
the performance of your weather
like
normalization
this, you can't ever really take weather out of the equation when we can't really observe the absence of weather's contribution to air pollution. So the best we could do is really use multiple approaches and just see how well they coincide. So one of the approaches we used was to use an observational analog. So for days that were not as wet and windy in the same month, for example, you know, what was the ratio of the change in NO2 in that on that day compared to the wet and windy day? And that was one approach. And then the second approach was to use a chemical transport model that did not account for the emission change associated with COVID-19 and reproduce a tropomi-like NO2 column from that model. And in that way, we're able to remove meteorology from the equation using that counterfactual as well. So I think the best we can do right now is use multiple approaches and see how consistent they are. We actually showed that they are consistent in some cases, but not consistent in other cases. So we actually do have some more work to be done to try to understand why there were those differences. I will say, if I just go back to that plot here, that when you look across the 20 cities, the approaches if you look at the two green dots, those two approaches for accounting for both seasonality and meteorology were very consistent. But if you look at individual cities, there's quite a bit of spread. So again, I think still work to be done to understand why we see that spread. You know, when we have an observational record like tropomi, we also have challenges with these cities differing in terms of like the number of days of observations due to the cloudiness and such. So or snowy days. So in some cases, we actually didn't have that many days in the observational record to use.
So a question from David. In an earlier talk, it was mentioned about the relative health effects of NO2 falling and ozone
great
rising.
Question. I apologize.
Susan, do you have any comments on the health impact associated with that?
I think it depends on which health outcome we're looking at. So the estimates that I gave earlier of the pediatric asthma impacts, these are from chronic exposure, and this is a long-term health outcome. So we actually use annual average NO2 to generate these estimates, and that's what's used in the epidemiology studies as well. I'm guessing that this comment has more to do with acute effects, so daily changes in NO2 and what that might do to, say, hospitalizations or emergency department visits that exacerbate asthma, for example. And it's very difficult for epidemiology studies to tease out the influence of any one pollutant, given that we're all exposed in a messy atmosphere of multiple pollutants at the same time, as well as weather effects and pollen and other heat and other things. But the evidence is getting pretty clear for long-term exposure to NO2 that is contributing to pediatric asthma incidence independent of PM 2.5 or ozone. There may be something, actually I would venture to say there's likely something else in the traffic-related air pollution mixture that we're not measuring that actually is causing these asthma development effects. But it's sort of impossible to know that right now because we're not measuring it.
Questions in the chat, please post them now if you have them. So we were scheduled to close up at 4, so we're pretty close to being on time. We've got a few minutes left. If there are any questions for any of the speakers, then now's the time to ask. Otherwise, I'll invite Paul to come back, and if he's got anything further to add. Thanks, Susan, for the talk, by the way. I can't. No. Okay. I can't see any other questions coming in. So it just remains to thank all the speakers once again. Thanks very much for presenting today, and thanks also to you for joining the meeting. So Paul and I will be in touch about next year's ACSG meeting in due course, which we hope to have around a similar time of year. So thank you, everyone. Bye-bye.